All right, let's dive into this paper. Window equivalences via categorical SL2 actions. It's looking at derived equivalences specifically for these things called stratified Mukai flops. They're important in lots of different areas of math, and this paper connects some pretty powerful tools to understand them.
Yeah, what's really cool is that it brings together two totally different ways of thinking about these equivalences. You've got these geometric categorical SL2 actions on one hand, and then these like magic window categories coming from matrix factorizations on the other. And the paper shows how they're actually connected.
Okay, so to get us started, the paper starts with these, what they call twin spaces, cotangent bundles of Grassmannians. We're not just talking about points on a surface, but all the possible directions and speeds they could have at every point. And the Mukai flop is kind of like a surgery that connects these twins by creating a shared roof over a blown-up common section.
Right, but here's the catch. The obvious way to connect them, just using that shared roof, doesn't actually give you a natural equivalence of their derived categories. You need something more sophisticated, and that's where the categorical SL2 action comes in.
So SL2, if I remember right, is a Lie algebra, right? Usually used to describe symmetries in a linear setting. So how are they using it in this, like, categorical context?
It's like taking that blueprint for symmetry and applying it to categories instead of just vector spaces. So the E and F operations from simult, they get translated into functors between categories. The relations they satisfy still hold, but now they're telling you about relationships between objects and morphisms.
Oh, I see. And they use this to build a kind of bridge between the derived categories of our twin spaces. So what's the actual construction of this bridge? What does it look like?
They use something called a Rickard complex. You can think of it as a chain complex where each term is built from these E and F functors. It's like a set of instructions for how to combine these functors in a very specific way. And then by taking the convolution of this complex, they create a functor that gives the equivalence.
Convolution, oh, that sounds familiar. That's like from signal processing in other areas, right? Is it similar here?
It's analogous, yeah, in the sense that you're combining objects, but now it's happening in this categorical world. Equation 9 in the paper, it gives you the actual formula for this convolution. Basically tells you how to glue together the pieces of the Rickard complex.
Okay, so that's one side of things, the categorical SL2 action. What about these magic windows? How do those fit into all of this?
The magic window approach that comes from viewing our cotangent bundles as symplectic quotients. It's a way to create new spaces by identifying points that behave the same way under a certain group action. And this leads to a connection with Landau-Ginzburg models, which physicists use to describe systems by their potential energy.
So we're going from geometry to physics now. This paper is all over the place.
Yeah.
But what about the windows themselves? What makes them so magical?
So in magic window theory, you're looking for special subcategories of the derived category. They're called window subcategories that behave nicely, particularly well. These subcategories are defined by certain ranges of parameters, which you can kind of think of as windows. And the magic is that for certain windows, these subcategories become equivalent to the derived category of the symplectic quotient. So it's a powerful tool to study it.
And the paper connects this to the SL2 stuff. That seems like a big leap.
That's the cool part. Theorem 1.1 in the paper, it actually links the categorical SL2 action to a specific magic window. It says that the equivalence you get from convolving the Rickard complex is actually the same as the equivalence given by this magic window, like finding a secret tunnel connecting two castles.
Whoa, that's really something. It really does suggest these two approaches are different sides of the same coin. But how do they actually construct these equivalences? Where does the rubber meet the road, so to speak?
That's where the paper gets into the real nitty-gritty. They use this idea of Heck correspondences, which are specific geometric objects that relate different Grassmannians. These correspondences, they define the E and F functors of the SL2 action, but in a really concrete way.
So it's like they're giving you the blueprints for how to actually build those E and F machines.
Precisely. And they go a step further by using Knörrer periodicity. It's like a dictionary that translates between the world of sheaves, which are geometric objects, and the world of matrix factorizations, which are algebraic objects. So it lets them express everything in the language of matrix factorizations, which is where the magic window theory really shines.
Oh, okay. That translation seems pretty crucial. So what kind of words are in this dictionary? What kind of translations does it provide?
For example, theorem 2.6, that tells us that the derived category of coherent sheaves on a singular space is equivalent to the derived category of graded matrix factorizations on a related space. So they can go back and forth between these two worlds using whichever language is, most convenient.
So they use this dictionary to express the functors of this SL2 action in terms of these matrix factorizations.
Exactly. Lemma 3.7 and proposition 3.8, they give you the actual matrix factorization kernels that realize these functors in the magic window world, like the nuts and bolts that make the whole thing work.
Okay, we're starting to see how this all fits together now, but why is this so important? What's the big takeaway from this connection between SL2 actions and magic windows?
One of the key implications is highlighted in corollary 3.6. It shows that certain important bundles, called Schur functors, are invariant under the equivalence. These Schur functors are like fundamental building blocks for understanding the geometry of these spaces. The fact that they're invariant tells us that the equivalence is preserving something essential about their structure, like saying that even though you're looking at these spaces through different lenses, certain core features stay the same.
Oh, that's really interesting. It makes it sound like this equivalence isn't just a mathematical curiosity, but a deep reflection of the geometry, the underlying geometry. And I have a feeling this is just the tip of the iceberg. What else is there to uncover in this paper?
Well, that's a good place to pause for now. We've set the stage, explored these twin spaces, the SL2 action, and these magic windows. But the real journey starts when we get into the heart of the proof and see how these seemingly different ideas are actually connected. Ready to go deeper? Welcome back.
So just to recap, we've got these cotangent bundles of Grassmannians, our twin spaces, and we know they can be connected in this subtle way using this categorical SL2 action. Gives us an equivalence of their derived categories. And we've seen some hints that it's connected to this whole magic window perspective, where certain subcategories capture essential information about these spaces.
Right. That connection is really striking. Like theorem 1.1 felt like a bolt from the blue, showing us that the equivalence from the Rickard complex is basically the same as a specific magic window equivalence. But how do they actually prove something like that? It seems like a pretty tough problem. It is. And the proof hinges on this key concept, the grade restriction rule. This rule gives us a precise way to characterize the objects that belong to a particular magic window subcategory. It's like, think of it as a membership card that only, certain objects in the derived category have.
Okay, so it tells us who's allowed in the club, so to speak. But how does that relate to the SL2 action and the equivalence we're trying to understand?
The key is to show that the convolution of the Rickard complex, which we've been calling T, that it respects this grade restriction rule. In other words, if you apply T to an object that's in a certain window subcategory, the result should also be in the corresponding window subcategory on the other side of the Mukai flop.
So it's like T is a well-behaved guest at the club.
Right.
Right. It only moves objects between, compatible rooms.
Exactly. But to prove this, they take this interesting detour through something called the quasi-symmetric model. This model is kind of a simplified version of the space of quiver representations we're really interested in. It's like, instead of looking at the whole building, you're just looking at a blueprint. But it still captures the key features we need.
Oh, okay. So we're trading complexity for clarity, right?
Yeah.
Right. But how do we know that we're not losing anything important in the process? How can we be sure that what we learn in this simplified model actually applies to the original, more complicated setting?
That's a great question, and the paper addresses that very carefully. They show that this quasi-symmetric model, it still has all the important structures we care about, including the categorical SL2 action. And importantly, the grade restriction rule actually has a much simpler form in this model.
So it's like we're working with a smaller version of the problem, but without losing any of the important details.
Precisely. And so by proving that the convolution of the Rickard complex satisfies the grade restriction rule in the quasi-symmetric model, they can then lift this result back to the original setting. It's a powerful technique that mathematicians use a lot to deal with really complex problems.
Okay, that makes sense. Kind of like building a scale model of a bridge to test its strength before you build the real thing, right? So let's Well, let's get a little more into the mechanics of this categorical SL2 action. You mentioned earlier that the E and F operations, which usually act on vector spaces, now they're acting as functors between categories. So how do these functors actually work? What's going on under the hood?
These functors are defined using integral kernels. They're kind of like blueprints for how to transform objects in the derived category. You can think of them as like mathematical machines that take an object as input and produce a new object as output.
So they're like functions, but operating on a more abstract level.
Exactly. And these kernels are constructed very carefully. The paper gives the actual formulas for the kernels of the E and F functors, and they involve some sophisticated geometric objects like Heck correspondences and determinant line bundles.
Wow, that sounds pretty intense. Can you break those down a bit?
Yeah.
What are Heck correspondences and determinant line bundles, and why are they popping up here?
So Heck correspondences are these geometric objects that relate different Grassmannians. They're like bridges connecting these spaces. They play a key role in defining the E and F functors. And determinant line bundles are they're objects that capture information about the orientation of a space. Like you can think of them as arrows attached to each point telling you which way is up.
Oh, I see. So we're using all of these sophisticated geometric tools to build the machinery for our SL2 action.
That's a great way to put it. And the way these Heck correspondences and determinant line bundles appear in the kernels, it's very precise. It makes sure that the E and F functors have the right properties, that they satisfy the relations of the SL2 Lie algebra.
It's amazing how these abstract algebraic concepts are being like realized through these very concrete geometric constructions. It's like we're watching the interplay between algebra and geometry like right in front of us. Now, you mentioned that the paper also talks about adjoints for these E and F functors. So what are adjoints in this context? Are they like inverses of the functors?
Adjoints are a fundamental idea in category theory. They're kind of like the best approximations to inverses. So sometimes a functor doesn't actually have a true inverse, but it might have an adjoint.
Mm-hmm.
And the adjoint captures some of the properties of an inverse.
So it's like a shadow of an inverse, doing its best to undo what the original functor did.
That's a great way to think about it. And in this case, the E and F functors, they're actually bi-adjoint, which means they're both left and right adjoints of each other, like a pair of dancers, each mirroring the movements of the other.
That's a beautiful image. So why is this bi-adjointness so important? What role does it play in the overall picture?
The bi-adjointness of the E and F functors, it's crucial for being able to construct the Rickard complex, which, if you remember, is the key to proving the main theorem of the paper. It's like a chain of these functors linked together very specifically, and their bi-adjointness ensures that this chain behaves the way it should, and it gives us that equivalence of derived categories that we want.
Okay, so the Rickard complex is like this carefully crafted necklace, right? With the E and F functors as the beads, and their bi-adjointness is what keeps the necklace from falling apart.
Exactly. And then by taking the convolution of this complex, you're basically collapsing it down into a single functor that like embodies the whole categorical SL2 action. This master functor is what gives us the equivalence between the derived categories of our cotangent bundles of Grassmannians.
This has been quite a journey. We've gone into the grade restriction rule, explored this quasi-symmetric model, and even looked into the machinery of the E and F functors and their adjoints. It's really amazing how much is packed into this paper, but I feel like there's still more to come. What else is waiting for us in this mathematical landscape?
You're absolutely right. There's still more to explore. In the next part, we'll really untangle the connection between the categorical SL2 action and the magic window theory. We'll see how the convolution of the Rickard complex actually manifests as a specific window equivalence. And we'll look at the implications of this result, including its connection to the invariance of Schur functors and its potential for further research.
Sounds like we're headed for a grand finale, where all these different threads will come together into something beautiful. I can't wait to see how it all unfolds. All right, so we're back for the final act of our deep dive into window equivalences via categorical SL2 actions. We've seen how these seemingly totally different concepts like Mukai flops, SL2 actions, and magic windows are all like intertwined, but there's still this one big question. How does that categorical SL2 action actually give rise to a specific magic window equivalence?
That's where the paper's big finish comes in Theorem 3.3. This theorem, it's the culmination of all the machinery we've been talking about, and it says that the equivalence we get from convolving the Rickard complex, which we've been calling T prime, it's exactly the same as a particular magic window equivalence. It's like, finding that secret passage connecting two different wings of a castle.
That's amazing. It's like we've been on these two separate paths, each with its own like twists and turns, and then suddenly they converge at this incredible view. But I gotta say, the proof of this theorem still feels a little mysterious. How do they actually show that connection?
Yeah, the proof is it's pretty intricate. It really relies on understanding the kernels of the functors involved. Remember those Ian functors? They're the building blocks of the Rickard complex. And their kernels are like blueprints for how they transform objects in the derived category.
Right. Right. We even saw those explicit kernels expressed in the language of matrix factorizations, thanks to Lemma 3.7, Proposition 3.8. They seem pretty complex with all those geometric things like Heck correspondences and determinant line bundles.
Exactly. And the key to the proof is to really analyze those kernels, but under Knörrer periodicity. That periodicity, remember, it's like a dictionary between sheaves and matrix factorizations.
So they use this dictionary to see the hidden structure of the kernels in the magic window world.
Right. They show that the kernels, when you look at them through Knörrer periodicity, they have a very specific form. And that form directly corresponds to the structure of the magic window equivalence. It's like taking an X-ray of those kernels and seeing the skeleton of the magic window equivalence right inside them.
Wow, that's incredible. It's like those kernels were hiding the code for the magic window equivalence all along, and Knörrer periodicity was the key to unlocking it.
Yeah, it's a really cool example of how different mathematical tools can, work together to reveal these deep connections. And the paper doesn't stop there. It goes on to explore some really interesting consequences of this theorem.
Okay, so let's get into those consequences. What else comes out of this connection between the SL2 action and magic windows?
One really striking consequence, it's highlighted in Corollary 3.5. It shows that the square of the equivalence T, the one we get from the Rickard complex, that it's actually a window shift autoequivalence.
Hold on. Let's clear that down. What does it mean for an equivalence to be a window shift autoequivalence?
So an autoequivalence is basically a symmetry of a category, a way to transform objects in that category while preserving its structure. And a window shift autoequivalence, it means that applying T twice is the same as shifting the window that defines our magic window subcategory, like sliding your window along a parameter space and seeing all these different but equivalent views of the geometry.
So it's like T is this shifting mechanism. It lets us explore all these different perspectives within the derived category, but we always stay within that essential equivalence.
Yeah, that's a great way to think about it. And it suggests there's this deeper structure, the symmetry behind these equivalences. Like there's a whole family of them, each one corresponding to a different window on the same geometry.
Fascinating. It opens up so many possibilities. And what about Corollary 3.6? What does that one tell us?
So Corollary 3.6, that one focuses on these special bundles called Schur-functors. They're like fundamental building blocks for understanding the geometry of these spaces. And the corollary shows that certain Schur-functors are actually invariant under the equivalence induced by the Rickard complex.
Invariant, meaning like they're fixed points under this categorical transformation.
Exactly. It's like even though the equivalence is shifting our perspective, changing things around in the derived category, these Schur-functors stay the same. They're like landmarks, providing a sense of stability while everything else is moving.
That's really cool. It makes it sound like this equivalence isn't just randomly shuffling things, but it's preserving some really fundamental parts of the geometry, like a dance where some of the dancers stay still while others move around them.
I love that analogy. And that invariance of the Schur-functors, it really points to the deep connection between the categorical cell 2 action and the underlying geometry. It tells us this equivalence isn't just a mathematical trick, but it's reflecting something really fundamental about these spaces.
Wow, this has been an incredible journey. We've gone through the world of Mukai flops, explored categorical SL2 actions, and seen the magic of window equivalences. It's amazing how all these different ideas have come together, to show this profound connection.
It really is. It's a testament to the power of math and how elegant it can be. And, I think this paper is just the beginning. The insights and techniques that they've developed here, They could unlock so many more mysteries and lead to new discoveries in all sorts of areas of math.
I couldn't agree more. This deep dive has really opened my eyes to a whole new world of mathematical possibilities. And I hope it's inspired our listeners to start their own exploration to discover the joy and wonder that's at the heart of math. So keep questioning, keep exploring, and keep pushing those boundaries.
And remember, even in the most abstract parts of math, there's always beauty to be found, connections to be made, and stories waiting to be told. Happy exploring, everyone.
All right, let's dive into this paper, Window Equivalences via Categorical SL2 Actions.
Sounds good.
This paper is a deep dive into derived equivalences
Yeah.
and how they work with something called a stratified Mukai flop.
Okay.
This flop connects the cotangent bundles of Grassmannians.
Interesting.
We'll be looking at this from two different perspectives. One using geometric categorical SL2 actions, and the other using these magic window categories.
Yeah, right. It's fascinating how the paper connects those two approaches.
Yeah.
It builds on a lot of work by, mathematicians like Namikawa, Kaudis, Kemnitzer, and Licata.
Yeah.
Especially their work on understanding these categorical SL2 actions and how they lead to derived equivalences.
Okay, so let's start with the basics. Grassmannians and their cotangent bundles.
Yeah.
You can think of a Grassmannian as like a space that parameterizes all the possible k-dimensional subspaces of an n-dimensional vector space.
Right.
For example, like the Grassmannian GR2 would represent all the planes that live within a four-dimensional space.
Exactly, yeah. And a cotangent bundle of a space, in this case the Grassmannian,
Right.
can be thought of as, adding information about the velocity or momentum at each point in the Grassmannian. It's a way to enrich the geometric structure and capture more information.
Okay, so we've got our Grassmannians and we've got their cotangent bundles. Now, what about this flop business?
Yeah.
Sounds kind of dramatic.
Well, it is a bit of a geometric surgery, but a very controlled one. The flop we're dealing with here is a stratified Mukai flop. It's a way to transform one space, in this case a cotangent bundle of a Grassmannian, into another related space. This transformation isn't arbitrary. It has specific properties that make it interesting to study.
And the paper says that like a straightforward approach using the so-called incidence variety doesn't quite give us the equivalence that we're looking for.
The incidence variety, which they denote zelo, gives us a correspondence between the two spaces. But it doesn't induce an equivalence of their derived categories. We need something more refined to capture the full picture.
Okay, so enter the Rickard complex.
Exactly.
This complex, denoted theta, is constructed using these additional correspondences, Z, I, for I from 1 up to the minimum of k and n minus k.
Exactly. These extra correspondences capture more subtle geometric information that's missing from that naive correspondence Z0.
So how does the paper approach this? The introduction mentions two main perspectives.
Yeah, that's one of the most interesting things about this paper. It explores this derived equivalence from two seemingly distinct viewpoints. The geometric approach using those categorical SL2 actions, and then the more algebraic magic window approach using categories of graded matrix factorizations.
Okay, so let's start with the preliminaries, where the paper introduces Nakajima quiver varieties.
Okay.
These quiver varieties are a powerful way to represent the cotangent bundles of Grassmannians. They let us view these bundles as hyperkähler quotients, which is a fancy way of saying that they inherit a rich geometric structure. So to be clear, a quiver variety is constructed from a quiver, which is really just a directed graph. But in this case, the quivers are particularly simple. They just have a single vertex and no edges. And because there are no edges, there's no linear maps to worry about. So a representation of this quiver just amounts to assigning a vector space to that single vertex. And then the quiver variety is constructed by taking a hyperkähler quotient of a space associated with these representations. And the paper says that this specific quiver variety is isomorphic to the cotangent bundle of the Grassmannian that we're interested in.
Exactly. This connection between quiver varieties and cotangent bundles of Grassmannians is a key ingredient in the geometric approach to understanding the derived equivalence.
So we're starting to see how this paper connects ideas from different areas of math, derives categories, algebraic geometry, and representation theory.
Absolutely. And that's one of the things that makes this work so compelling. It brings together tools and perspectives from different fields to shed light on a fundamental geometric problem.
Let's move on to section 3, where the paper really dives into the heart of the geometric categorical error SL2 action. They introduce these functors, E and F, that act on the derived category of coherent sheaves on these cotangent bundles of Grassmannians. Sounds a bit like a magic trick.
Yeah.
You take a sheaf, apply one of these functors, and poof, you get a new sheaf.
It is a bit like a magic trick, but a very precise one. These functors are not arbitrary. They satisfy specific relations that mirror the structure of the Lie algebra SL2.
Okay.
That's where the name categorical SL action comes from.
So the SL2 part refers to a specific Lie algebra, which is a mathematical object with a lot of structure.
Right.
And these functors, E and F, are mimicking that structure
Exact.
in the world of derived category.
Exactly. And this connection to the Lie algebra SL2 gives us a way to understand the behavior of these functors and how they relate to the derived equivalence.
Okay, so these functors, E and F, are like the main actors in this geometric drama.
Right.
And they're governed by the rules of SL2, which acts as a sort of director behind the scenes. But how do these functors actually work? They're built using kernels, right?
That's right. These kernels are geometric objects that encode the information needed to transform one sheaf into another. You can think of them as blueprints for the transformations performed by the functors E and F.
And the paper gives a very concrete example of how these functors act in the case of the cotangent bundles of Grassmannians, right?
Yes, they illustrate how E and F act on specific sheaves, demonstrating the intuitive meaning behind the mathematical formalism.
So we've got our functors, our kernels, and our SL2 action. How do these all come together to create the derived equivalence?
That's where the Rickard complex comes in. The paper shows that a specific convolution of the Rickard complex induces the desired derived equivalence between the cotangent bundles of Grassmannians related by the flop.
So the Rickard complex is like the conductor of this mathematical orchestra.
Exactly.
It's coordinating all the different elements to produce a harmonious result.
Exactly. And the proof that this convolution induces the equivalence is where things get really interesting. It involves a delicate interplay of techniques from homological algebra and algebraic geometry.
Okay, let's unpack that proof a bit. The first step seems to be showing that a certain functor is fully faithful, which basically means it preserves all the information about the objects and the morphisms in the category.
Right. They show that the functor phi, which is given by tensoring with the convolution of the Rickard complex, is fully faithful. This is a crucial step in establishing the equivalence because it means that phi embeds the derived category of one cotangent bundle into the derived category of the other without losing any information.
And to prove this fully faithfulness, they use the key lemma, lemma 3.7, which calculates the kernels of certain functors related to the Rickard complex.
Yes. Lemma 3.7 is the workhorse of this part of the proof. It provides a very concrete description of these kernels, which allows them to analyze the behavior of the functor phi and show that it's fully faithful.
So it's like we're peering under the hood of the Rickard complex, examining its internal workings to understand how it performs this transformation.
Exactly. And by understanding these kernels, we gain a deeper insight into the structure of the derived equivalence itself.
The next step in the proof is to show that this functor phi is also essentially surjective. What does that mean?
Essentially, surjective means that up to isomorphism, every object in the target category is the image of an object in the source category under the functor phi. In other words, phi covers the entire target category, ensuring that nothing is missed.
So it's like making sure that our map covers the entire territory, leaving no gaps or unexplored regions.
Precisely. And together, fully faithfulness and essential surjectivity imply that phi is an equivalence of categories, which is the ultimate goal.
And to prove this essential surjectivity, they use a specific resolution of a certain sheaf, which is constructed using Schur functors.
Right.
These Schur functors seem to pop up everywhere in this paper.
They do. Schur functors are incredibly versatile tools in representation theory, and they play a crucial role in understanding the structure of the objects involved in the derived equivalence.
Okay, so we've established that the functor phi, given by tensoring with the convolution of the Rickard complex, is an equivalence of categories. What are the implications of this result?
This equivalence tells us that the two cotangent bundles of Grassmannians related by the stratified Mukai flop are equivalent from the perspective of derived categories. It means that the categories of coherent sheaves on these two spaces carry the same information,
Right.
even though the spaces themselves are different geometrically.
So it's like we found a hidden dictionary that allows us to translate between the languages of these two spaces, revealing their underlying similarities.
Exactly. And this equivalence has implications for understanding the geometry of moduli spaces. Moduli spaces are spaces that parameterize certain geometric objects, and derived equivalences can provide powerful tools for studying their structure.
And the paper explores some of these implications in corollaries 3.5 and 3.6, right?
Yes. Corollary 3.5 relates the derived equivalence to spherical twists, which are specific types of autoequivalences of derived categories.
Okay.
This connection suggests a deeper relationship between the derived equivalence constructed in this paper and other geometric transformations. And Corollary 3.6 examines how Schur functors behave under the derived equivalence. It shows that certain Schur functors are, in a sense, invariant under the equivalence, which provides further insight into the structure of the categories involved.
So it's like we're uncovering hidden symmetries and patterns in the world of derived categories.
Absolutely.
And these symmetries reflect deeper geometric structures.
Absolutely.
Yeah.
And to make things more concrete, they even discuss a special case where k equals 1 in remark 3.4. This case corresponds to a simpler geometric setup, and it illustrates the theorem's implications in a more accessible way.
Okay, so we've gone through the geometric approach to the derived equivalence,
Right.
focusing on categorical SL2 actions and the Rickard complex. Now, what about the magic window approach, using categories of graded matrix factorizations?
That's where things get even more interesting. The paper establishes a connection between the geometric approach and the magic window approach,
Okay.
showing how they both lead to the same derived equivalence. But to understand this connection, we need to delve into the world of matrix factorizations.
Sounds good. Let's continue this deep dive and explore those matrix factorizations.
Okay. All right. So let's switch gears a bit and delve into this magic window approach. This approach uses categories of graded matrix factorizations to try to understand this derived equivalence.
Okay, so what exactly are matrix factorizations? I remember seeing that term mentioned earlier.
Right.
But it all sounded a bit like a foreign language.
Well, you can think of a matrix factorization as like a way to represent a function, usually a polynomial, as a product of two matrices. More formally, a matrix factorization of a polynomial f in a ring R consists of two square matrices, A and B, with entries in R, such that their product AB is equal to f times the identity matrix.
So it's like we're factoring the polynomial, but instead of using numbers, we're using matrices.
That's a great analogy. And just like with factoring numbers, there can be multiple matrix factorizations for the same polynomial.
And how do these matrix factorizations connect to derived categories?
Well, it turns out that you can construct a category out of the matrix factorizations of a given polynomial. The objects are the matrix factorizations themselves, and the morphisms are given by certain maps between the matrices.
So we're taking this algebraic concept of matrix factorization and turning it into a categorical object. And this category is somehow related to the derived category of coherent sheaves on our cotangent bundles of Grassmannians.
Precisely. The paper establishes a connection between these two seemingly disparate worlds.
Wow, that's incredible. But how do we bridge the gap between geometry and algebra? It seems like a huge leap to go from sheaves on spaces to matrix factorizations.
It is a significant leap, but the paper lays out a pretty clear path. They show that the kernels of the functors in the Rickard complex, which we talked about earlier in that geometric setting, can be translated into the language of matrix factorizations. They provide explicit formulas for these kernels in terms of matrices.
So it's like we're building a dictionary, mapping geometric objects like kernels to their algebraic counterparts. Matrix factorization.
Exactly. And this dictionary allows us to move seamlessly between the two perspectives, leveraging the strengths of each approach.
Okay, so we've got our matrix factorizations and this connection to the geometric kernels. Now, what about this magic window business? How does that fit into the picture?
The magic window refers to a specific subcategory within the category of matrix factorizations. This subcategory is defined by certain grade restriction rules, which act as a filter, selecting only certain matrix factorizations that satisfy specific properties.
So it's like we're putting on a special pair of glasses that allows us to see only a particular subset of the matrix factorizations, those that are relevant to the derived equivalence.
That's a great way to think about it. And the paper shows that the convolution of that Rickard complex, after appropriate restrictions, lands precisely within this window subcategory.
So it's like the Rickard complex, acting as our trusty mutation machine, is transforming matrix factorizations in a way that aligns with the rules of the magic window.
Precisely. And this connection between the Rickard complex and the window subcategory is a key ingredient in establishing the window equivalence.
Now, before we get to the window equivalence itself, the paper dives into this specific type of model called the quasi-symmetric model. Why introduce this model? It seems like we're adding another layer of complexity.
Well, the quasi-symmetric model is actually designed to simplify things. It's a specific representation of a group that makes it easier to apply what's called magic window theory, which provides a framework for understanding derived categories of GIT quotients. These are spaces obtained by taking quotients of certain spaces by group actions.
So it's like we're choosing a particular coordinate system. A specific way of looking at the problem that makes the calculations and the analysis more manageable.
Exactly. And the paper carefully describes the setup of this quasi-symmetric model, highlighting its key properties and how it relates to the other constructions.
Okay, so we've got our quasi-symmetric model. Now, how does this model connect to the grade restriction rules that define the magic window?
That's where Kempfness stratifications come in.
Kempfness stratifications.
These stratifications provide a way to decompose the unstable locus of the quasi-symmetric model into a collection of strata, each characterized by specific properties of the group action. And these strata are directly related to the Guy weights that determine the grade restriction rules.
So it's like we're breaking down the quasi-symmetric model into smaller pieces, and each piece corresponds to a particular set of grade restriction rules.
Exactly. And this connection between the Kempfness strata and the grade restriction rules is crucial to understanding how the magic window subcategory fits within the larger category of matrix factorizations.
Okay, so we've got our quasi-symmetric model, our Kempfness stratifications, our grade restriction rules, and our connection back to the Rickard complex. How does all of this machinery come together to give us the window equivalence?
That's the exciting part. In the next section, we'll see how the Rickard complex, acting as this mutation machine, interacts with this intricate structure to construct the window equivalence and reveal the fascinating connections between these different subcategories of matrix factorizations.
Sounds like a grand finale. I'm ready for the curtain to rise on this mathematical masterpiece. Okay, so how does this window equivalence actually work? We've laid out all the pieces: the Rickard complex, matrix factorizations, grade restriction rules, the quasi-symmetric model, Kempfness stratification. So how does it all fit together?
Well, it's all about creating a specific correspondence, a way to translate between two different views of these matrix factorizations. Like, you can think of it like having two windows, each showing a different perspective on the same underlying mathematical landscape. The window equivalence provides a way to map what you see through one window to what you see through the other.
So it's not about making the two views identical, but more like finding a way to relate them consistently, like a map that helps you navigate between two different regions that are still connected somehow.
Exactly. And the key to constructing this map is the Rickard complex. Remember, we showed how the convolution of the Rickard complex can transform these matrix factorizations, bringing them into that magic window subcategory.
Right, those matrix factorizations that follow those specific grade restriction rules. So the Rickard complex is acting like a bridge builder here, connecting the two sides of this window equivalence.
Exactly. Now, to prove that the convolution of the Rickard complex actually induces the window equivalence, the paper lays out two conditions that need to be satisfied. The first condition is that the kernel of the functor, induced by the convolution, should restrict to the diagonal on the product of the semi-stable locus with itself. This ensures that the equivalence acts as the identity when restricted to this locus.
So it's like checking that if you look straight through a window, you see a reflection of yourself, not something completely different, right? The equivalence shouldn't distort the view within a given window.
Exactly. And the second condition is that the essential image of the functor induced by the kernel lies within the window subcategory. This makes sure that the equivalence respects the grade restriction rules, meaning it only maps to objects that belong to the designated window on the other side.
Okay, so like making sure that our bridge is only connecting to valid destinations, right? Those that satisfy the specific criteria defined by those grade restriction rules.
Precisely. And the paper very carefully verifies that the convolution of the Rickard complex satisfies both of these conditions. Lemma 3.13 tackles the first condition, showing that the convolution restricts to the diagonal, just like we expect.
Okay, so we've confirmed that our bridge has a solid foundation on both sides. Now we need to actually test the bridge itself, right? Make sure it's leading to those right destinations within the window subcategory.
That's where theorem 3.3 comes into play. It establishes the second condition, proving that the essential image of the functor, induced by the convolution, lies within the window subcategory. This theorem relies heavily on that detailed analysis of the Rickard complex and its convolution that we did earlier.
It's really amazing how all these different parts, derived categories, categorical actions, matrix factorizations, grade restriction rules, Kempfness stratifications come together in this proof of the window equivalence. It's like we've built this really complex machine with each component playing this crucial role in achieving this final result.
Absolutely. And this result is really significant for understanding the geometry of moduli spaces. Remember, moduli spaces are the spaces that parameterize certain geometric objects. The window equivalence gives us this powerful tool for studying these spaces, allowing us to relate different moduli spaces that might seem really different at first glance.
So like we've discovered this hidden connection between mathematical objects that seem totally unrelated. And this connection opens up all these new ways of exploring and understanding.
Precisely. And the authors even suggest that there might be an even simpler kernel that could induce the window equivalence in this case. So that suggests there's still more to uncover, more elegant and efficient ways to construct these equivalences.
It's amazing to think that even after such, a detailed and intricate analysis, there might be even deeper levels of simplicity and beauty just waiting to be discovered.
That's the beauty of mathematics. There's always more to learn, more connections to make, and more mysteries to solve. This paper is just one step in a much larger journey of exploration and discovery.
So to wrap up, what are the key takeaways for our listeners?
I'd say this paper really highlights how powerful derived equivalences are as tools for understanding geometry. These equivalences help us connect seemingly different spaces and reveal those hidden similarities between them. This specific case with the stratified Mukai flop and the window equivalence, it shows how these abstract ideas can be applied to concrete geometric problems, leading to all sorts of new insights and connections.
And the paper also shows how different areas of math can work together, right? Algebraic geometry, representation theory, category theory, all working together to illuminate this complex and really fascinating problem.
Exactly. It really is a testament to the unity and interconnectedness of mathematics, where seemingly disparate ideas converge to create this harmonious and elegant whole.
This deep dive has definitely been a whirlwind tour of some pretty advanced mathematical concepts. But I think we've all come away with this much deeper appreciation for just how beautiful and powerful mathematics can be.
Absolutely. And I hope this has sparked some curiosity in our listeners to, explore further into this world, to explore the countless connections and uncover all the hidden patterns that are out there in our mathematical universe.
So until our next deep dive, keep exploring, keep questioning, and keep marveling at all the endless wonders of mathematics. All right, so today, we're going to be taking a deep dive into some really fascinating mathematics. We're talking about window equivalences via categorical SL2 actions. And you've given us a research paper that explores derived equivalences. And let me tell you, this is not your average algebra.
Yes, it is not your average algebra problem.
Okay.
This paper is a journey into a world where seemingly different mathematical structures are very intricately connected. It's like discovering hidden passageways between seemingly separate landscapes.
Okay, so to start off, the paper focuses on cotangent bundles of Grassmannians. And these are like complex, multidimensional spaces. And there's this special transformation called a stratified Mukai flop. That essentially flips
Yeah.
one of these spaces into another.
Right, and what's really fascinating is that while these flip spaces look different, their underlying mathematical essence, represented by their derived categories of coherent sheaves, remains the same. Imagine rearranging a room.
Okay.
All the furniture moves, but the room itself stays the same.
Got it. So it's like the essence of the space is preserved even though it undergoes this flop.
Yeah.
But here's where it gets interesting. The paper explores two different ways of understanding
Exactly.
is mathematical sameness after the flop.
Exactly. One approach utilizes what's called geometric categorical SL2 actions.
Okay.
Think of it as a way to understand how certain symmetries act on these categories.
Okay.
And these symmetries kind of govern how things can be transformed
Got it.
while keeping their fundamental properties.
Okay, so it's like a set of rules that dictate how these categories can change without losing their core identity.
Precisely.
What about the second approach?
The second approach uses what's called magic window theory. It's a way to analyze these categories by breaking them down into smaller,
Got it.
more digestible pieces. Imagine looking through different windows to understand the layout of a large building.
Interesting.
Each window gives you a different perspective, but together they reveal the whole structure.
So two completely different ways of looking at the same mathematical phenomenon.
Yes.
And this paper connects them.
Yeah, and that's where it gets exciting.
Okay.
The author shows that the Rickard complex, which arises from the categorical SL2 action, is equivalent to a specific window equivalence within the magic window framework. And this connection provides a deeper understanding of both approaches and sort of illuminates the underlying mathematical structure.
All right, this is definitely getting me intrigued.
All
now
right.
let's really get into the details and see how these concepts unfold in the paper.
Yeah.
The paper sets the stage by introducing the notation for Grassmannians.
Yes. So it starts with K, SEN, which represents the space of all k-dimensional subspaces within a cn-dimensional complex vector space. For example, GR2C5 represents all two-dimensional subspaces in a five-dimensional complex space.
Okay, that's straightforward enough. So GRKCN is like a catalog of all possible k-dimensional subspaces within a larger cn-dimensional space.
Exactly.
Yes.
Then the paper introduces GRTSNK, the Grassmannian of k-dimensional quotients of Cn.
Okay.
And this is isomorphic to GRN, KCN, highlighting the duality between subspaces and quotient spaces.
Ah, so there's two ways to look at these Grassmannians.
Yes.
Either as spaces of subspaces or as spaces of quotients.
Right.
And they are essentially equivalent.
Yes.
This duality seems to be a recurring theme in the paper.
Yeah, indeed. And the author utilizes both notations throughout the paper to provide different perspectives and insights into the problem. The focus then shifts to the cotangent bundles of these Grassmannians, which are denoted as TAs, CN, and CN.
Now, cotangent bundles, those are a bit more complex. Can you remind us what those are?
Think of a cotangent bundle as a way to capture information about the infinitesimal changes or velocities at each point in our Grassmannian.
Right.
So imagine you're moving along a surface. The cotangent bundle describes all possible directions and speeds you could have at any point.
Okay, that makes it a bit more intuitive.
Okay.
So it's like adding another layer of information to each point in our Grassmannian, telling us about the potential movements at that point.
Exactly.
Right.
Now, the paper highlights that both TJCN and TJRCN are symplectic resolutions of a specific nilpotent orbit closure denoted as N.
Okay.
This means that they both provide ways to smooth out the singularities present in N.
So it's like taking a crumpled piece of paper, N, and finding two different ways to flatten it out.
Exactly.
Smoothly.
Yes, a very good analogy.
Represented by T-chair, KCN, and T-chair, CN.
Yeah. Now, the paper goes on to explain the stratified Mukai flop, which relates these two resolutions through a specific process. Okay.
It starts by blowing up the zero sections of both cotangent bundles.
Hold on. What exactly is a zero section in this context?
The zero section is a special subspace within the cotangent bundle where all the velocities are zero.
Okay.
It's like being at a standstill on that surface we imagined earlier.
Got it.
Yeah.
So we blow up these zero sections.
Yeah.
What happens then?
This blow-up results in a common space, which the author denotes as Z0. Which essentially glues together the two resolutions in a specific way.
Okay.
However, the author points out that Z0 itself is not enough to establish a natural equivalence between the derived categories of the two resolutions.
Okay.
We need to consider other spaces as well,
Okay.
which the author denotes as ZI, which arise from the fiber product of the blowdowns of the zero section.
I was like finding additional bridges between our two smoothed out landscapes.
Precisely.
And these bridges, the ZIs, are crucial for understanding how the categories are equivalent.
Now, let's explore the two approaches to understanding this equivalence.
Okay.
The first approach, using categorical SL2 actions, involves constructing a special complex called the Rickard complex.
Okay.
All right, let's break down this Rickard complex. What's so special about it?
So the Rickard complex is built using functors, which the author denotes as E and F.
Okay.
These functors act on the derived categories, and they're analogous to the raising and lowering operators in the representation theory of SL2.
Okay, I remember those in quantum mechanics.
Yes.
They move us between different energy levels. So are these functors moving us between different levels in the category?
That's a great way to think about it.
Okay.
Yeah, and the Rickard complex combines these E and F functors in a specific way. It's their convolution, which the author denotes as T. That ultimately provides the equivalence between the derived categories.
So it's like the Rickard complex is a recipe. And when you cook it, you get this T, which is the key to unlocking the equivalence.
Exactly. The paper describes the Rickard complex as a categorification of the decomposition of the reflection element of SL2 acting on the weight spaces of an irreducible representation of SL2. Essentially, it's bringing a higher level of structure and meaning to this algebraic concept.
Fascinating.
Yeah.
Now, what about the magic window approach?
Okay.
How does that fit into the picture?
The magic window approach utilizes a technique called graded matrix factorizations. This allows us to analyze the derived categories by focusing on the singular parts of our geometric spaces, which surprisingly contain crucial information about the structure of the derived category.
That's counterintuitive.
It is counterintuitive, yeah.
Usually singularities are the parts mathematicians try to avoid.
Very true. But in this case, the singularities are key. And the magic window helps us to extract information from them.
Got it.
In a very controlled and elegant way. Think of our derived category as a vast landscape. The magic window is a specific region within this landscape that we choose to focus on. It's defined by a parameter which the author calls Bowman, which determines the size and position of the window.
So it's like looking through a carefully chosen window to see a specific part of the landscape.
Yes.
And by changing, we can adjust our view.
Exactly.
What's remarkable is that for each choice of bone, we get a subcategory of the derived category. That's equivalent.
That's equivalent to the original.
So the original one.
Yeah, and the paper shows that one of these window subcategories is actually equivalent to the derived category we get after the Mukai flop.
Wow, so we can understand the effect of this complex transformation, the Mukai flop, by simply shifting our focus within the original derived category.
Yes.
That's a powerful concept.
It is a very powerful concept, and the paper goes even further, showing a direct connection between the convolution of the Rickard complex, T, and this specific window subcategory. The author proves they are, in fact, equivalent.
So these two approaches, which seemed completely different at first, ultimately lead to the same result.
Exactly.
That's a pretty profound connection.
Yes.
What are the implications of this connection?
Well, this connection deepens our understanding of both categorical SL2 actions and the magic window theory. It reveals sort of hidden symmetries and structures within the derived category that wouldn't be apparent otherwise. It's like discovering a secret passageway between two seemingly separate rooms in a mansion.
I'm completely hooked.
Oh,
Let's unpack the specifics of how this connection is established.
Right.
The paper delves into Nakajima quiver varieties. Can you tell us what those are and how they come into play?
Nakajima quiver varieties are a class of geometric spaces that are constructed using quivers, which are mathematical diagrams consisting of vertices connected by arrows. Think of them as visual representations of relationships between different objects, like a family tree where each person is a vertex and the arrows represent relationships.
I see.
Yeah.
So how do we go from these quivers
Oh.
to actual geometric spaces?
So it's a bit intricate, but essentially you start with a quiver,
Okay.
and then you assign vector spaces to each vertex
Okay.
and linear maps
Okay.
to each arrow.
Hmm.
This data, along with some additional choices,
Okay.
like a stability parameter,
Okay.
determines a geometric space called a Nakajima quiver variety.
Okay.
It's like assembling a Lego structure.
I love that analogy.
Oh, good.
From a blueprint.
Okay.
The vector spaces and linear maps are the Lego pieces.
Yes.
And the stability parameter tells you how to put them together.
It's
Okay, so how do these quiver varieties relate to our cotangent bundles of Grassmannians?
Well, the cotangent bundles of Grassmannians we've been discussing
Yeah.
can actually be realized as specific examples of Nakajima quiver varieties. The paper uses this perspective to translate the problem of derived equivalence
Yep.
into the language of matrix factorizations,
Okay.
which is the natural domain of the magic window theory.
So it's like we're using the quiver varieties as a bridge
Yes.
between the geometry of the cotangent bundles
Yeah.
and the algebra of matrix factorizations,
Yeah.
allowing us to apply the magic window theory to solve our original problem.
Exactly.
That's really starting to blow my mind.
Okay.
Now let's zoom in on the machinery of matrix factorizations.
All right.
The paper mentions an equivalence called Knörrer periodicity.
Okay.
Can you explain what that is?
Knörrer periodicity connects the derived category of a singular space,
Okay.
like the zero section of our cotangent bundle, to the derived category of matrix factorizations on a related space
Okay.
called the Landau-Ginzburg model.
Okay.
Think of it as a mathematical dictionary that allows us to translate between these two languages.
Okay, I'm getting a sense of it, but can you remind us what a Landau-Ginzburg model is?
Imagine a space equipped with a special function called the superpotential.
Okay.
Okay. In our case, the Landau-Ginzburg model is built from the data of the Nakajima quiver variety. And the superpotential comes from the moment map.
Right, the moment map.
Yeah.
It's a key part
It is.
of the quiver variety construction.
Yes.
But what's the significance of this superpotential?
The superpotential essentially encodes the singularities of the space.
Okay.
It tells us where the space is badly behaved, mathematically speaking.
Got it.
And the matrix factorizations provide a way to understand the behavior of the derived category in the presence of these singularities.
So it's like the superpotential is a map of the danger zones in our space. And the matrix factorizations are the tools we use to navigate those zones safely.
Another great analogy.
Knörrer periodicity essentially tells us that understanding the derived category of the singular space is equivalent to understanding the derived category of matrix factorizations
Yes.
on the Landau-Ginzburg model.
Exactly.
So we can switch between these two perspectives, the language of sheaves on the singular space and the language of matrix factorizations on the Landau-Ginzburg model without losing any information.
Right.
That's quite a powerful tool.
It is, yeah.
Now, let's go back to the magic window itself.
Okay.
How do we choose that parameter that
Right.
defines the window?
The choice of Ginzburg is subtle.
Okay.
It needs to be generic,
Right.
meaning it must avoid certain bad values
Okay.
that would lead to problems in the theory.
Got it.
It's like navigating a ship through a treacherous strait.
Okay.
We need to carefully choose a course to avoid running aground.
I see. So how do we find those safe passageways?
The paper provides specific conditions to ensure that the magic window works as intended.
Okay.
In the case of cotangent bundles of Grassmannians, the choice of tune-on corresponds to selecting a specific interval of integers.
An interval of integers.
It is, yes.
That sounds surprisingly simple.
It is,
Okay.
but the implications are profound. This interval determines the weights of the representations that appear in the window subcategory,
Okay.
which ultimately determines the objects that are visible through the window.
So it's like we're filtering the landscape based on the colors of the objects.
Yeah.
And the interval of integers tells us which colors are allowed
Right.
through the window.
Yes.
And we're looking for the window
Yes.
that shows us the objects that are equivalent to the derived category after the Mukai flop.
Precisely.
Yeah.
The paper shows that the specific window subcategory that's equivalent to the derived category after the Mukai flop corresponds to a particular choice of this interval.
So by carefully choosing our window, we can isolate the parts of the derived category
Precisely.
that are most relevant to understanding the effects of the flock.
Exactly.
That's fascinating.
It is, yes. And it highlights the power of the magic window theory to reveal subtle structures and connections within the derived category.
Now let's explore the specifics
All right.
of how the author connects
Good.
the Rickard complex to the magic window subcategory.
Okay.
The paper introduces something called Heck correspondences.
Okay, so imagine you have two Grassmannians,
Okay.
GRMCN and GRNCN,
Right.
where M is less than N.
Okay.
So we're talking about spaces of subspaces with different dimensions.
Okay.
The Heck correspondence, which the author denotes as Zn M, can be thought of as a space that sits between these two Grassmannians. Connecting them in a specific way, it helps us understand how objects on one Grassmannian can be transported to the other.
So it's like a bridge between two islands, allowing us to travel back and forth.
Yes, and what's crucial for our story is that the kernels of the functors E and F in the Rickard complex are actually supported on these Heck correspondences.
Okay, kernels.
Yes.
Can you remind me what those are in this context?
The kernel of a functor is kind of like its essential ingredient.
Okay.
It describes how the functor acts on objects.
Okay.
And the fact that these kernels are supported on the Heck correspondences means that the action of E and F is intimately tied to the geometry of these connecting spaces.
So the functors are like chefs.
Okay.
And the Heck correspondences are there kitchens where the magic happens?
I like that.
Okay.
The paper uses Knörrer periodicity to translate these kernels into the language of matrix factorizations, allowing us to analyze them.
Within the magic window framework.
Okay.
And these translated kernels have special properties.
Okay. What kind of special properties are we talking about?
One crucial property is that these translated kernels are supported on the same space, which the author denotes as weary n, which can be viewed as a Heck correspondence between the Landau-Ginzburg models associated with the two Grassmannians.
So it's like the Knörrer periodicity has transported the Heck correspondence from the world of Grassmannians to the world of Landau-Ginzburg models.
Exactly.
This transported Heck correspondence, weary n, plays a vital role in understanding how the Rickard complex interacts with the magic window subcategory.
Exactly.
Specifically, the convolution of the Rickard complex, T, can be seen as a sequence of mutations within the derived category of matrix factorizations on mutations. What do those involve in this context? Think of a mutation as a surgical procedure on an object in the derived category. It modifies the object in a controlled way while preserving some of its essential properties.
Got it.
The convolution of the Rickard complex, T, is like a series of these mutations, each corresponding to applying a specific functor from the Rickard complex.
So T is like a skilled surgeon.
Yes.
Meticulously reshaping objects in the derived category through a series of carefully chosen mutations.
Exactly.
Where do these mutations lead us?
That's the remarkable part. These mutations transform the objects in a way that aligns them perfectly with the magic window subcategory.
So the Rickard complex is like a guide leading us through the landscape of the derived category. Transforming objects along the way until we reach the promised land of the magic window subcategory.
Precisely. And this connection between the Rickard complex and the magic window subcategory offers a very deep and insightful explanation for why the derived categories of the two cotangent bundles are equivalent after the Mukai flop.
Okay, I'm following the logic here. But can we take a step back and recap the key points we've discussed so far? It's a lot to take in.
Here's a summary. The problem is that we're exploring how the derived categories of two cotangent bundles of Grassmannians are equivalent after a transformation called the stratified Mukai flop. Approach 1 is categorical SL2 actions. This approach uses functors analogous to raising and lowering operators to construct the Rickard complex, whose convolution, T, gives us the desired equivalence. Approach 2 is magic window theory. This approach uses Knörrer periodicity to translate the problem into the language of matrix factorizations on the Landau-Ginzburg model. And the magic window lets us focus on specific subcategories. equivalent to the original derived category.
Okay.
The connection is that the paper demonstrates
Okay.
that the Rickard complex and the magic window subcategory
Okay.
are equivalent. They're
Yeah.
connected through mutations
Yeah.
within the derived category of matrix factorizations.
Okay. That's a helpful summary.
Good.
Now let's unpack the specifics
Right.
of how this connection is established.
Okay.
The paper mentions GIT quotients.
Okay.
What are those, and how do they relate to the Hicknight correspondences?
GIT quotients,
Okay.
or geometric invariant theory quotients,
Okay.
are special types of geometric spaces
Okay.
obtained by taking the quotient of a space
Okay.
by a group action.
Okay.
Think of it as averaging out the symmetries
Got it.
in a space.
Okay.
In this case, we are looking at the action of
Okay.
the general linear group, GLV,
Okay.
on a space of linear maps.
Okay. So it's like we're identifying points that are equivalent
Yes. And
under these symmetries.
Okay.
The stability conditions used to define the GIT quotient
Okay.
determine which points are considered stable
Okay.
and which ones are unstable.
Okay.
The Heck correspondences
Yeah.
turn out to be the spaces
Okay.
obtained by taking the quotient of the stable points.
So it's like we're filtering out the bad points that don't behave well
Exactly.
under the group action
Yeah.
and keeping only the good ones.
Exactly.
Hmm.
And this perspective is crucial
Okay.
because it allows us to analyze
Okay.
the structure of the kernels
Yeah.
of E and F,
Yeah.
which, as we discussed, are supported
Right.
on these Heck correspondences.
So we're using the group action and
Yeah.
the stability conditions
Yeah.
to dissect the Heck correspondences,
Really?
revealing their inner workings
Exactly.
and how they determine the action of the functors.
Yes.
This is starting to feel like a detective story.
It is a bit, yeah.
Okay, now the next step
Okay.
is to apply the Knörrer periodicity.
To translate these kernels
Yes.
into the language of matrix factorizations.
Exactly.
We use a special matrix factorization called the Koszul factorization
Yes.
to lift the kernels
Yes.
from the singular space to the Landau-Ginzburg model.
Exactly.
Right, the Koszul factorization, our mathematical elevator
Yeah.
that transports objects between these two different worlds.
Yes.
But how exactly does this lifting process work
Okay.
for the kernels of E and F?
So it's a bit technical,
Okay.
but essentially you use the Koszul factorization to create a new object
Okay.
on the Landau-Ginzburg model
Okay.
that mirrors the behavior of the original kernel on the singular space.
Okay.
It's like creating a 3D print of a sculpture. The print captures the essential shape and features of the original,
Okay.
but it's made of a different material.
That's a helpful analogy.
Okay.
So we've created these 3D printed versions of the kernels
Yeah.
on the Landau-Ginzburg model.
Uh-huh.
What do we do with them?
The paper shows that these lifted kernels are supported on the same space
Okay.
that Willen, which we talked about earlier.
Right. It's like the Knörrer periodicity took the Heck correspondence along for the ride when it lifted the kernel.
Exactly. And this transported Heck correspondence, Willen N, plays a crucial role in connecting the Rickard complex
Okay.
to the magic window subcategory.
Okay.
It turns out that the convolution of the Rickard complex, T, can be viewed as a sequence of mutations within the derived category.
Okay. I remember we talked about mutations earlier,
Yeah,
but
yeah.
can you remind me what those are?
Yeah, so a mutation is kind of like a surgical procedure on an object in the derived category. It modifies the object
Okay.
in a controlled way
Yeah.
while preserving certain essential properties and the convolution of the Rickard complex.
Yeah.
T can be seen as a series of these mutations, each corresponding to applying a specific functor from the Rickard complex.
So P is like a master sculptor,
Yes.
carefully chiseling away at an object,
Yeah.
transforming it step by step,
Yeah.
until it reveals its final form.
Exactly.
What's the significance of these mutations taking place
Yeah.
on this transported Heck correspondence?
Yeah.
WLM.
That's the key insight.
Okay.
The fact that the mutations take place on WLM ensures that the transformed objects end up landing within the magic window subcategory. In other words, the convolution of the Rickard complex, T, is like a guided tour
Okay.
through the derived category that ultimately leads to the magic window subcategory.
Wow, that's amazing. So it's like the Rickard complex is not only giving us the equivalence between the derived categories,
Yeah.
but also providing a specific path
Right.
within the derived category.
Exactly.
That leads us to the magic window subcategory.
Yeah, and this connection
Okay.
between the Rickard complex and the magic window subcategory provides a deep and insightful explanation for why the derived categories of the two cotangent bundles
Okay.
are equivalent after the Mukai flop.
Okay, I'm really starting to appreciate the elegance and power of this paper. The author has woven together so many different mathematical concepts to create a beautiful and intricate tapestry of ideas, but my brain is starting to feel a bit overloaded.
Sure.
Can we summarize the key takeaways from what we've discussed so far?
Absolutely. So the main points are, number one, the problem.
Okay.
We're exploring how the derived categories of two cotangent bundles of Grassmannians are equivalent after undergoing a stratified Mukai flop,
Okay.
approach one. Categorical SL2 actions.
Okay.
This approach constructs the Rickard complex, and its convolution T gives us the equivalence.
Got it.
Approach 2, magic window theory.
Okay.
This approach uses Knörrer periodicity and magic window subcategories to understand the equivalence.
Got it.
And then finally, the connection.
Okay.
The paper shows a remarkable connection between the Rickard complex and a specific magic window subcategory.
Okay.
With the convolution, T, acting as a bridge between them, and this connection is established through a series of mutations within the derived category of matrix factorizations. On the transported Heck correspondence, will and nen.
That's a great summary.
Good.
It really highlights the beauty and complexity of the ideas presented in this paper.
Yes.
Now let's delve even deeper
Okay.
into the technical details of the paper.
Right.
We've mentioned grade restriction rules.
Okay.
What are those, and how do they fit into this picture?
The grade restriction rules are crucial
Okay.
for characterizing the objects that belong to the magic window subcategory. Remember, the magic window subcategory is defined by the parameter,
Right.
which corresponds to an interval of integers.
Yes.
These rules tell us which objects have weights that fall within the specific interval.
Okay.
It's like having a membership card for the Magic Window Club.
Okay, so it's like a filter that ensures only objects with the right weights are allowed in.
Exactly.
How are these grade restriction rules defined?
They're defined using a special stratification of the Landau-Ginzburg model.
Okay.
I imagine we're slicing a cake into layers, each with its own unique characteristics.
Okay.
In this case, the stratification is defined using one-parameter subgroups of the group GLV,
Okay.
each corresponding to a specific way of scaling the vector space V.
Scaling, like stretching or compressing the base.
Exactly, yes. The stratification is based on how points in the Landau-Ginzburg model behave
Okay.
under these scaling actions. It's like shining different colored lights on the model, and each light reveals a different layer.
Okay, so we've sliced the Landau-Ginzburg model into these layers using these scaling actions.
Yes.
How do we get from that to the grade restriction rules?
The grade restriction rules are defined in terms of the weights of objects.
Weights.
Yeah.
We talked about those earlier.
Res.
In the context of representations.
Exactly. In this context, the weight of an object tells us how it transforms under the scaling actions defined by the one-parameter subgroups. The grade restriction rules essentially state that only objects with weights falling within a specific range determined by the parameter are allowed in the magic window subcategory.
So it's like setting a weight limit for entry into the magic window club.
Yeah.
Only objects within a specific weight range are granted access?
A very good analogy.
Okay.
And the paper shows that the convolation of the Rickard complex, T, actually satisfies these grade restriction rules.
Okay.
This is a crucial step in proving that T is equivalent to the magic window subcategory.
So T passes the weight test and is officially a member of the magic window club.
Exactly.
This connection between the Rickard complex and the grade restriction rules seems really important.
It is. It provides a concrete way to see why T lands in the magic window subcategory.
Okay.
It's like we've mapped out the precise path that T takes through the derived category. And we can verify that this path leads directly to the magic window subcategory.
This is all incredibly insightful.
Good.
But before we move on,
can
you elaborate on how exactly we determine the weights of objects in the derived category? It still feels a bit abstract.
Sure. The weights of objects are determined by their behavior under the action of the group GLV. Each one-parameter subgroup of GLV corresponds to a particular scaling action. And the weight of an object tells us how much it stretches or compresses under that specific scaling action.
So it's like measuring how elastic each object is under different types of stretching.
That's a good way to think about it. And the grade restriction rules essentially define a weight limit for objects allowed into the magic window subcategory. Only objects with weights that fall within the specified range determined by the parameter are granted access.
That makes sense. And the fact that T satisfies these grade restriction rules confirms its membership in the magic window subcategory.
Precisely. And this confirmation is a key step in establishing the equivalence between the Rickard complex and the magic window subcategory, demonstrating that these two seemingly different approaches ultimately converge to the same result.
This is truly a remarkable paper.
Yeah, it is.
Weaving together such a diverse range of mathematical concepts in such a sophisticated and elegant way.
It is a testament to the power and beauty of mathematical thinking.
Now, I know we've been talking about the abstract concepts quite a bit.
Sure.
But I'm curious, can you give us a concrete example of how these ideas work in practice?
Of course. Let's consider the case where K1, this corresponds to the cotangent bundles of projective spaces.
Projective spaces. Those are like spaces of lines passing through the origin.
Yes.
I remember those from geometry class.
Exactly. And in this case, the Heck correspondences are just points.
The
Landau-Ginzburg model is also quite straightforward. And the matrix factorizations are relatively simple.
So it's like a simplified model. Where we can really see the machinery at work.
Exactly.
Without getting bogged down in too much complexity.
Precisely. And in this simplified setting, the author explicitly computes the convolution of the Rickard complex, T, and shows that it's equivalent to the structure sheaf.
The structure sheaf?
Yes.
Isn't that one of the most fundamental objects?
It is.
In algebraic geometry.
It is. It's like the simplest possible sheaf you can imagine. And the fact that such a simple object embodies the equivalence between the derived categories is quite remarkable.
That's incredible. So even in this toy model setting, the connection between the Rickard complex and the magic window subcategory is deep and insightful.
It is,
I'm feeling much more grounded now that we've seen a concrete example.
Good.
Now, I'm ready to delve deeper into the technical details how these equivalences are established. The paper mentions Lascaux resolutions and semi-orthogonal decompositions. Can you tell us more about those?
Lascaux resolutions are powerful tools used to resolve sheaves on flag varieties. Remember, flag varieties are spaces that parameterize chains of subspaces within a given vector space. The Grassmannian, or KCN, is an example of a flag variety.
So it's like a space of all possible ways to arrange subspaces within a vector space.
Exactly.
And these Lascaux resolutions help us to untangle complex sheaves on these flag varieties.
Exactly. Lascaux resolutions provide a way to break down complex sheaves on flag varieties into simpler pieces, making them easier to analyze. It's like taking apart a complicated machine to understand how its individual components work.
I'm following you. And the author uses these Lascaux resolutions to analyze the kernels of the functors E and F.
Exactly. By applying Lascaux resolutions, the author reveals that the kernels have a particularly nice structure that can be expressed as direct sums of vector bundles.
Vector bundles. They seem to be popping up everywhere.
They are, yes.
In this paper.
They're very fundamental objects in algebraic geometry, and they provide a very convenient way to represent information about linear maps and transformations. In this case, the decomposition of the kernels into vector bundles makes the analysis much more manageable.
So it's like we've taken apart a complicated clock and found that it's made up of neatly arranged gears and springs. Now, what about semi-orthogonal decompositions? Those are like a divide and conquer strategy for understanding. Like dividing a kingdom into smaller, more manageable provinces. A semi-orthogonal decomposition splits a triangulated category into smaller pieces called subcategories, which are orthogonal to each other in a specific sense. This orthogonality makes it easier to analyze the structure of the entire category by focusing on the individual subcategories.
So it's like breaking down a complex problem
Yeah.
into smaller,
Yes.
more manageable subproblems.
Exactly. And the author cleverly chooses
Okay.
a semi-orthogonal decomposition,
Okay.
where one of the subcategories
Okay.
is precisely the magic window
Ooh,
subcategory.
that's strategic.
It is, yes.
So by carefully choosing the decomposition,
Yes.
the author isolates the magic window subcategory
Precise.
within the larger derived category.
Exactly.
Okay.
This isolation allows the author to focus on the properties of the magic window subcategory
Okay.
and ultimately demonstrate that the convolution of the Rickard complex, T, belongs to this subcategory.
Yeah.
This is all starting to make sense. So the author uses Lascaux resolutions to analyze the kernels of the functors, then uses semi-orthogonal decompositions to break down the derived category
Right.
and isolate the magic window subcategory.
Exactly.
And by carefully analyzing the action of T,
Yes.
the author demonstrates that it satisfies the properties of the magic window subcategory,
Precisely.
establishing the connection
Yes.
between the Rickard complex and the magic window approach.
Exactly. It's a beautiful and intricate argument that weaves together a diverse range of mathematical techniques to reveal a deep and insightful connection.
This has been an incredible deep dive so far.
Good.
I'm really starting to grasp the power and elegance of the ideas presented in this paper.
Okay.
But I think we'll need to continue this exploration in our next session.
Okay.
My brain needs a little time to process
Sure.
all this amazing information.
I agree. This is a rich and rewarding paper that deserves careful study and contemplation.
Okay.
I look forward to continuing our discussion in our next session. It is like taking the tools we've developed for understanding Mukai flops and venturing into a whole new uncharted territory.
So it's like taking the tools we developed for understanding Mukai flops and venturing into a whole new uncharted territory.
Precisely, this opens up exciting new avenues for research and suggests that the ideas presented in this paper have far-reaching implications beyond the specific problem of Mukai flops.
It's fascinating how even highly specialized mathematical research can have these unexpected ripple effects.
Absolutely. This interconnectedness of mathematical ideas is a testament to the beauty and power of the field.
Now, I know we've been primarily focused on understanding the technical details of the paper, but I'm curious, what are some of the broader implications of this work? Does it have any connections to other areas of mathematics or even to theoretical physics?
That's a great question. The work presented in this paper has potential connections to several other areas of mathematics, including representation theory, algebraic geometry, symplectic geometry, and even string theory.
Wow, that's quite a diverse range of fields. Can you elaborate on those connections a bit further?
Certainly. In representation theory, which studies the ways in which groups can act on vector spaces, the categorical SL2 actions used in this paper have close ties to the representation theory of the Lie algebra SL2. The Rickard complex, which is a key object in the paper, can be viewed as a categorification of a certain decomposition in the representation theory of SL2.
So it's like the paper is lifting a concept from representation theory to a higher level of abstraction.
Exactly, and this connection to representation theory provides a deeper and more insightful perspective on the derived equivalences induced by the Mukai flop.
Fascinating.
Yes.
What about the connections to algebraic and symplectic geometry?
In algebraic geometry, which studies geometric objects defined by polynomial equations, the paper's focus on cotangent bundles of Grassmannians connects it to the study of moduli spaces, which are spaces that parameterize certain types of geometric objects. The Mukai flop itself is a transformation that relates different moduli spaces, and understanding this transformation is a central problem in algebraic geometry.
Okay, so the paper is contributing to a deeper understanding of these moduli spaces and the relationships between them. What about symplectic geometry?
Symplectic geometry studies spaces equipped with a special kind of structure called a symplectic form. Cotangent bundles are naturally symplectic manifolds, and the Mukai flop can be viewed as a symplectic transformation. The techniques developed in this paper could potentially be applied to study other symplectic transformations and their effects on derived categories.
So it's like we're opening up a new toolkit for symplectic geometers.
Precisely. Now, the connection to string theory is perhaps the most intriguing, though also the most speculative. String theory is a theoretical framework in physics that attempts to unify all the fundamental forces of nature. In string theory, D-branes are extended objects that play a crucial role in the theory. The derived categories of coherent sheaves have been shown to have deep connections to the physics of D-branes, and the results presented in this paper could potentially provide new insights into these connections.
Wow, that's mind-blowing. It's amazing to think that these abstract mathematical concepts could have implications for our understanding of the universe at its most fundamental level.
It is. Of course, the connections to string theory are still largely conjectural, and much more research is needed to explore them fully. But the potential is certainly there.
Well, this deep dive has been an incredible journey, and I'm feeling both intellectually stimulated and inspired by the vastness and interconnectedness of the mathematical landscape we've explored.
It's been a pleasure to join you on this adventure, and as always, the journey of mathematical discovery never truly ends. There's always more to explore, more connections to uncover, and more beauty to appreciate.
Thank you for being such an insightful and engaging guide. Until next time, keep exploring the wonders of the mathematical universe. Welcome to the Deep Dive.
Oh.
Today, we're going deep into some pretty advanced mathematics.
Oh, yeah.
Exploring a paper that connects derived equivalences and categorical SL2 actions.
Cool.
We're looking at an excerpt from Weissi's window equivalences via categorical SL2 actions. Even the title is pretty intense, but I'm excited to learn more.
It's a fascinating area of mathematics where seemingly different geometric objects turn out to be connected in really profound ways. And representation theory, with its focus on symmetries, it gives us this powerful framework to uncover these connections.
Okay, you've already piqued my curiosity, but let's not get ahead of ourselves.
Yeah.
Could you explain what a derived equivalence is in this context? It sounds very abstract.
Imagine you have two geometric spaces that look completely different on the surface.
Okay.
A derived equivalence means that their categories of sheaves, which essentially capture the ways functions behave on these spaces, are essentially the same. It's like discovering that two seemingly different novels actually tell the same story.
Yeah.
Just using different characters and settings.
That's a great analogy. So we're looking for hidden similarities between spaces that might appear very different at first glance. And what about these categorical SL2 actions? What role do they play in all of this?
Think of SL2 as a set of symmetries.
Okay.
Like rotations or reflections. A categorical SL2 action lifts these symmetries to act on categories, in this case, categories of sheaves. This action allows us to construct these special objects called Rickard complexes, which act like bridges, connecting the categories of sheaves of seemingly different spaces and revealing the hidden derived equivalences.
So we're looking at how the symmetries of SL2 can help us build these bridges between categories. The paper mentions cotangent bundles of Grassmannians. Can we start by breaking down what those are?
Absolutely. Grassmannians are fundamental objects in geometry. You can think of the Grassmannian gray as the set of all k-dimensional subspaces or flats sitting inside a larger n-dimensional complex vector space.
Okay.
It's a way of systematically organizing all the possible k-dimensional slices of a larger space.
Okay, so it's like choosing a line in a plane, but in a much more general setting. And what about these cotangent bundles? What do they add to the picture?
The cotangent bundle of a space,
Right.
like a Grassmannian, gives us a way to attach additional directions to each point, representing all possible velocities a point in the space can have. Imagine attaching a little arrow to each point on the Grassmannian, indicating its potential movement.
Okay.
This turns it into a symplectic manifold, a type of space with very nice geometric properties that are often studied in physics.
Interesting. So we're adding more information to the Grassmannian, but considering all possible movements at each point. The paper focuses on two specific cotangent bundles, TAK-AJK, Sienna, and TAAZK, COGK. Why these two?
That's where it gets really interesting. While they might seem different, they're actually related through a process called a stratified Mukai flop. This is like performing a carefully controlled geometric surgery, using a series of blow-ups and blow-downs to transform one space into the other. This suggests a deep connection between these two cotangent bundles, even though they appear distinct at first glance.
A geometric surgery. That's a powerful image.
Yeah.
So we have these two spaces that are related by this flop. What role does the categorical SL2 action play in revealing their connection?
The categorical SL2 action gives us the tools to build a bridge between the derived categories of these two cotangent bundles. This bridge is called a Rickard complex, and it's constructed using the functors that arise from the SL2 action.
So the SL2 action provides the building blocks for this bridge.
Yes.
the Rickard complex. And this complex helps establish the derived equivalence between the two spaces,
Right.
showing that their categories of sheaves are essentially the same.
Exactly. But there's another fascinating way to visualize this connection, and
Gotcha.
it's called the magic window.
The magic window, that sounds intriguing.
Think of the magic window as a filter that highlights the essential objects in our derived categories. It's a region defined using the weights of the representations that appear in our spaces, telling us which objects are well-behaved and how to match them up between the two cotangent bundles.
Okay, so the magic window helps us see which objects on each side are the key players in this derived equivalence. So we have the Rickard complex, built from the categorical SL2 action, and the magic window. How do they work together?
The beauty of Say's work is that he shows how these two concepts are deeply connected. The objects matched by the Rickard complex are precisely those whose weights lie inside the magic window. The magic window gives us a visual way to see the derived equivalence established by the Rickard complex.
So the magic window and the categorical SL2 action are two sides of the same coin, both revealing the hidden derived equivalence between these cotangent bundles. That's a pretty amazing connection.
Absolutely. And to understand how this works in detail, we need to delve deeper into the specific structure of these cotangent bundles. It turns out they can be described using objects called Nakajima quiver varieties.
Nakajima quiver varieties. I'm familiar with quivers, but how do they help us understand these geometric spaces?
Quiver varieties are a powerful way to represent geometric spaces using diagrams. Imagine you have a quiver, which is basically a directed graph. You associate vector spaces to the nodes of the quiver and linear maps to the arrows. This turns a diagram into a geometric space that captures the information encoded in the quiver.
So it's like turning a visual representation into a concrete geometric object. How does that apply to the cotangent bundles of Grassmannians?
It turns out that the cotangent bundles we're interested in can be constructed as specific types of quiver varieties called Nakajima quiver varieties. Let's start with a simple quiver with just one node and no arrows. To this node, we associate two vector spaces, a k-dimensional complex vector space, Vk, and another vector space, Cn. We then consider a space, xk, which consists of pairs of linear maps, one going from Vk to Cn and another going back from Cn to V.
I'm visualizing this. So xk is the space of all these pairs of maps going back and forth through Vk and Cn.
Yeah.
What's the next step in constructing the cotangent bundle?
We introduce a group, Gian, which is the group of invertible linear transformations of Vk. This group acts on xk by changing the basis of Vk, essentially rotating or rescaling the vector space, Vk, within those pairs of linear maps.
Okay, so we have this group action on xk. What's the significance of this?
The cotangent bundle of the Grassmannian Gia, Grk, Cn, can be constructed as a quotient of xk by j. But to get a nice space with good geometric properties, we also need to impose a special condition called a stability condition.
A stability condition. What role does that play?
Think of it as selecting a well-behaved subset of xk before taking the quotient by Gink. The stability condition ensures that the resulting quotient space, which will be our cotangent bundle, has the desired geometric properties. In this case, we use two specific stability conditions, denoted 8 plus NE, which lead to the cotangent bundles TGRKCN and TGRCNK, respectively.
So by using the same quiver but different stability conditions,
Right.
we get those two different cotangent bundles that are related by the stratified Mukai flop.
Exactly.
It's amazing how these seemingly abstract concepts are starting to connect in such a concrete way.
That's the beauty of mathematics. We've gone from these abstract-sounding cotangent bundles of Grassmannians to a more tangible picture using quivers, group actions, and stability conditions. This framework will be crucial for understanding how the magic window and the categorical SL2 action work together to establish the derived equivalence.
I'm ready to dive deeper into the magic window. What can you tell me about its construction?
The magic window arises from the representation theory of the group geek. Remember, geek is the group of invertible linear transformations of Vk. Every representation of geek can be decomposed into irreducible representations, which are like the building blocks of representations. Each irreducible representation is associated with a weight, which is an element of a lattice.
So the weights are like labels for the irreducible representations. How do these weights lead to the magic window?
The magic window is a specific region in the weight lattice. To define it, we start with a zonotope, a geometric shape constructed using the weights of the representation xk, that space of pairs of linear maps we discussed earlier. Then we shift the zonotope by a special parameter, denoted by m sonotope, This shifted zonotope becomes our magic window.
So we have this geometric shape, the zonotope, which we shift to obtain the magic window. What's so magical about this window?
The magic lies in the fact that points inside the magic window correspond to the weights of well-behaved objects in our derived categories.
Okay.
These are the objects that will be matched up under the derived equivalence. Moreover, each dominant weight inside the magic window corresponds to an irreducible representation of Grank. These representations are crucial for understanding the structure of the derived categories.
So the magic window isn't just a random shape.
Yeah.
It's a carefully constructed region that highlights the crucial weights, the ones linked to the irreducible representations that play a key role in the derived equivalence.
Precisely. And the truly remarkable thing is that the derived equivalence induced by the Rickard complex can be described entirely in terms of the magic window. The objects that are matched up by the Rickard complex are exactly those whose weights lie inside the magic window.
So the magic window provides a visual representation of the derived equivalence. This is all incredibly fascinating, but I have to admit my head is starting to spin a little. We've covered a lot of ground, from cotangent bundles and quivers to stability conditions and magic windows. Is there anything else we need to establish before diving into the specifics of Seo's proof?
You're right, we've covered a lot of ground. There's one more crucial tool we need to introduce: matrix factorizations. They provide an algebraic framework that allows us to translate the geometric concepts we've been discussing into a language suitable for rigorous proofs.
Matrix factorizations. All right, lead the way.
Welcome back to our deep dive into the world of window equivalences. We've been exploring how the symmetries of Silil 2 can reveal hidden connections between seemingly different geometric spaces.
I'm eager to delve deeper into how these connections are actually proven. You mentioned matrix factorizations as a key tool for this. Can you remind me what those are and why they're so important in this context?
Absolutely. Remember, we discussed how those cotangent bundles of Grassmannians can be viewed as the zero sets of special functions called moment maps?
Yeah.
These moment maps, which capture information about symmetries, give rise to another type of function called a superpotential, which is defined on a space called a Landau-Ginzburg model.
Okay, I'm following so far. The cotangent bundles are linked to these Landau-Ginzburg models via moment maps and superpotentials.
Yeah.
But where do matrix factorizations come in?
Matrix factorizations provide a way to represent sheaves,
Right.
which capture information about functions on these Landau-Ginzburg models, even when those models have singularities, points where the space is not smooth.
So it's like extending the concept of a sheaf to spaces that might have these rough spots. Why is that necessary?
Many interesting geometric spaces, including those cotangent bundles we're studying,
Right.
have singularities. Matrix factorizations give us a way to work with these spaces despite their singularities, allowing us to use the powerful tools of homological algebra to study them.
Okay, that makes sense. So a matrix factorization is a way to represent a sheaf on these Landau-Ginzburg models. What does a matrix factorization actually look like?
A matrix factorization consists of two sheaves, let's call them F0 and F1, and maps between them: D0, F0 mass 1, D1, F1 mass F0. These maps, D0 and D1, satisfy a special condition. Their composition, D1, D0, and D0, D1, is equal to multiplication by the superpotential function, W. In other words, D1, D0x equals Wx for any element x in S0.
Okay.
And similarly for D0, D1.
So these maps wrap around and their composition is tied to the superpotential function. That sounds pretty abstract.
Yeah.
How does this relate to the derived equivalence between the cotangent bundles?
Remember those functors, E and F, which were the building blocks of the categorical SL2 action?
Right.
These functors act on the derived categories of the cotangent bundles.
Okay.
And we want to understand how they translate into the language of matrix factorization.
We want to see what E and F look like in this new algebraic world.
Exactly. And Sue's paper provides explicit constructions for matrix factorization kernels that represent these functors.
Kernels. What are those in this context?
In this setting, a kernel is a mathematical object that describes the action of a functor. Think of it as a blueprint for how the functor transforms objects from one category to another. Sue constructs specific kernels, which are themselves matrix factorizations that capture the actions of E and F on matrix factorizations.
So we've translated the geometric functors into algebraic kernels. What happens next?
The next step is to understand how these kernels behave when we compose the functors E and F.
Oh.
Remember the Rickard complex?
Yes.
It's constructed by composing these functors in a very specific way.
Yes, the Rickard complex was that chain of functors that gave us the derived equivalence.
Exactly. The remarkable insight is that when we convolve the kernels associated with the functors in the Rickard complex,
Okay.
we get a new kernel that induces the window equivalence.
Convolution. You have to explain that one.
Think of convolution as a way of combining the information contained in multiple kernels to get a new kernel. In this case, convolution takes those individual kernels, each representing a functor in the Rickard complex, and merges them into a single kernel that captures the essence of the window equivalence.
So we're essentially compressing the entire Rickard complex into a single kernel.
Yes.
And this new kernel gives us the window equivalence in the world of matrix factorizations.
You got it. And here's where the magic window makes its grand reappearance. The components of this new kernel are built from those special representations of the group GRAC whose weights lie inside the magic window.
It's amazing how the magic window keeps popping up in different contexts, first geometrically and now algebraically.
That's right. The magic window plays a central role in guiding this entire process. Now, to prove that this kernel actually induces the window equivalence,
Okay.
we need to show that it maps the correct objects to each other, and for that,
Yeah.
Sue introduces grade restriction rules.
Grade restriction rules, what are those?
Yeah. These rules impose constraints on the allowed weights of the objects that appear in the derived categories. They ensure that we're focusing on the well-behaved objects that are relevant to the window equivalence.
So it's like a quality control measure, making sure that the kernel doesn't introduce any rogue objects into the mix.
Exactly. And the crucial part of C's proof is demonstrating that the kernel obtained through convolution satisfies these grade restriction rules.
That sounds pretty intricate. How does he show that?
It involves a combination of geometric insights and algebraic manipulations. He starts by carefully analyzing the geometry of those Heck correspondences,
Right.
those special subvarieties that we use to define the functors E and F.
Right, they were like the geometric building blocks of those functors.
Precisely. C shows that the kernel obtained from the convolution can be extended to a larger space called the quasi-symmetric model.
Okay.
This larger space allows us to analyze the kernel's properties in a more convenient setting.
So we're going to a bigger space to gain a better perspective on the kernel.
Exactly. Think of the quasi-symmetric model as a larger canvas on which we can study these matrix factorizations. C proves that the extended kernel satisfies the grade restriction rules on this larger space.
Okay, so we've extended the kernel to this larger space and shown that it behaves nicely there. What happens next?
Then we restrict the extended kernel back to the original Landau-Ginzburg model. Because it satisfied the grade restriction rules on the larger space, it will automatically satisfy them on the smaller space as well.
So by taking this detour to the larger space, we've gained a key insight into the kernel's behavior on the original space.
That's right. And because the restricted kernel satisfies the grade restriction rules, we can conclude that it induces the window equivalence, meaning it matches up the correct objects in the derived categories, precisely those whose weights lie inside magic window.
Wow, this is starting to come together beautifully. We started with geometric objects and symmetries, translated them into the algebraic language of matrix factorizations, extended those matrix factorizations to a larger space, and then used the grade restriction rules to show that the restricted kernel gives us the window equivalence.
And remember, this is just one specific example of how these ideas can be applied. Derived equivalences, categorical actions, and magic windows are powerful tools for exploring hidden connections across a wide range of mathematical landscapes.
I'm ready to explore more. What other applications of these concepts are out there? Welcome back to our deep dive into the world of window equivalences. We've been on quite a journey exploring this intricate interplay between geometric spaces and symmetries and derived categories.
It's been a fascinating exploration, hasn't it? We've seen how these seemingly abstract mathematical concepts like categorical SL2 actions and magic windows can reveal these hidden connections between geometric objects like cotangent bundles of Grassmannians.
Absolutely. And we've learned how these connections can be made mathematically precise using the language of matrix factorizations. But I'm still a little fuzzy on the final steps of Sio's proof. How does he actually show that this kernel obtained through the convolution of the Rickard complex kernels really does induce the window equivalence?
It's a clever combination of geometric insights and algebraic manipulations. A key part of the proof involves understanding how the kernel behaves on a larger space called the quasi-symmetric model, and then restricting it back to the original Landau-Ginzburg model.
Right. You mentioned this quasi-symmetric model earlier. It's like a bigger canvas where we can study the kernel in a more convenient setting, right?
Precisely. The quasi-symmetric model is an ambient space that contains the original Landau-Ginzburg model. And Sue shows that the kernel we obtained through convolution can be naturally extended to this larger space.
Okay, so we have this extended kernel on the quasi-symmetric model. Why is this extension so important?
The key is that the grade restriction rules, which impose constraints on the weights of objects in the derived category, have a very natural interpretation in the context of the quasi-symmetric model. Remember, these rules ensure that we're focusing on the well-behaved objects that are relevant to the derived equivalence.
Right. Those rules act like a quality control measure, ensuring that we're working with the correct objects.
Exactly. And on this larger quasi-symmetric model, Sue proves that the extended kernel satisfies the grade restriction rules. This is a crucial step because it allows us to connect the behavior of the kernel on the quasi-symmetric model to its behavior on the original Landau-Ginzburg model.
Okay, I'm starting to see the strategy here.
Yeah.
We go to this bigger space, prove something nice about the extended kernel there, and then use that information to deduce something about the original kernel back on the smaller space.
Exactly. Once we know that the extended kernel satisfies the grade restriction rules on the quasi-symmetric model, we can restrict it back down to the original Landau-Ginzburg model. And because the grade restriction rules are compatible with this restriction process, we can conclude that the restricted kernel, which is the one we're ultimately interested in, also satisfies these rules.
So by taking this detour to the quasi-symmetric model, we gain a crucial piece of information. The restricted kernel obeys the grade restriction rules on the original space. But how does that finally lead to the proof that the kernel induces the window equivalence?
This is where everything comes together beautifully. Remember that the window equivalence is defined by a specific subcategory of the derived category of matrix factorizations, the window subcategory. The objects in this subcategory are the ones whose components are built from those special representations of Grank, whose weights lie inside the magic window.
Right. The magic window highlights the essential objects in our derived categories, the ones that will be matched up under the equivalence.
Exactly. And Serre shows that because the restricted kernel satisfies the grade restriction rules, it must send objects to objects within this window subcategory. In other words, the kernel respects the structure defined by the magic window. This is the final piece of the puzzle. It demonstrates that the action of the kernel on the derived categories is precisely the action that defines the window equivalence.
So it's like the kernel is guided by the magic window, ensuring that it maps objects in a way that's consistent with the window equivalence. This whole proof is a remarkable symphony of geometric intuition and algebraic precision. It's incredible how these seemingly disparate areas of mathematics come together to paint such a beautiful picture.
I completely agree. And what's even more exciting is that this is just the tip of the iceberg. The ideas of derived equivalences, categorical aptions, and magic windows have far-reaching implications in many areas of mathematics, from algebraic geometry and representation theory to mathematical physics and mirror symmetry.
Wow, this seemingly esoteric topic has opened up a whole universe of possibilities. It makes you wonder what other hidden connections might be lurking out there, waiting to be discovered.
That's the beauty of mathematics. There's always more to explore, always deeper connections to uncover. Who knows what other magic windows we might find as we continue our journey into the vast landscape of mathematical ideas.
Thanks for guiding us through this incredible mathematical adventure. I have a feeling this is just the beginning of our exploration of derived equivalences and their many wonders.
It's been my pleasure. Until next time.
All right, so we're diving into this paper today, window equivalences via categorical SL2 actions.
Yeah, it's a pretty fascinating look at derived equivalences.
Okay, so specifically, they're looking at this thing called a stratified Mukai flop.
Right, and it connects these cotangent bundles of Grassmannians.
Right, which, describe all the possible k-dimensional subspaces of an n-dimensional space.
Yeah!
And that, you've got the cotangent bundles on top of that, so you're attaching vector spaces to each of those subspaces.
Yeah, it's a lot of layers. It can get pretty abstract pretty quickly.
Right, but the authors, Kautis, Kamnitzer, and Licata, use this idea of a geometric categorical SL2 action to create a derived equivalence between these cotangent bundles.
Yeah, and they're really kind of seemingly unrelated if you just look at them at first glance.
Yeah, it's like finding a secret passage between two totally different mathematical worlds, or like a hidden tunnel connecting two cities.
I like that, yeah.
And then it gets even more interesting because they try to show us a shortcut through this tunnel using something called magic window categories.
Yeah, that's a great analogy. It's like they're giving us a simpler way to see these complex equivalences.
Right. So to kick things off, maybe we could start by breaking down what a stratified Mukai flop actually is.
Sure. So you can think of a stratified Mukai flop as a kind of surgery on a geometric space. It connects two different spaces, and in this case, it's those cotangent bundles of the Grassmannians that we were talking about.
Okay, so like reshaping the space without losing any material.
Exactly. And one of these cotangent bundles describes the k-dimensional subspaces of Cn, so GRK, CSCn.
And the other one describes the k-dimensional quotients.
Right, GRC and K. And the Mukai flop is like a bridge between those two.
Okay, so how do they actually build that bridge?
Well, the way they do it is by blowing up the zero sections of both cotangent bundles.
Okay.
And that creates this common space that they denote as Z0.
All right, so they both kind of meet there.
Kind of, but it turns out that Z0 isn't quite the right place to get the equivalence.
What? Really? I thought that was the whole point.
Well, you see, it's just the starting point. To actually establish the derived equivalence, they need to consider other components, which they call Z-air.
Okay, so there's like more to this relationship than we initially thought.
Yeah, it's not just a simple meet and greet at ZO.
It's more like a whole family reunion.
Exactly. All these other components, these ZIs, they play a role too.
Okay, so let's maybe move on to those geometric categorical is categorical actions.
Right.
I have to admit, even the name sounds kind of intimidating.
It's a mouthful, for sure.
Yeah. So could you break it down for us? What's going on there?
Sure. So it's basically using this, the representation theory of the Lie algebra, SLC here, to understand categories of geometric objects.
Okay, so we're talking about symmetries, transformations.
Exactly. And specifically, we're looking at the sheaves on these cotangent bundles.
Okay.
And the action part comes from using these special functors.
Right, those mathematical operations.
Right. They map objects from one category to another.
So they kind of move things around between categories.
Right. And in this case, they have these two important functors, E and F.
Okay.
And those act very much like the elements in the Lie algebra, the raising and lowering operators we see in representation theory.
So they're mimicking what's happening in the representation theory.
Yeah, pretty much.
Okay, so they've got these two functors, but how do you define those things? They don't just magically appear. Right?
No, of course not. They define them using kernels.
Okay.
And those kernels are special types of sheaves, and they're supported on those ZI components.
Oh, okay, so it connects back to the Mukai flop.
Exactly. They're all tied together.
So those kernels hold the geometric instructions for that SL2 action.
That's really cool. Okay, so then they go on to construct something called the Rickard complex, which they denote by the Greek letter theta.
Right.
So what exactly is this complex? Well, it's a sequence of functors connected by maps, which are called differentials. So you can think of it as a chain of instructions where each link in that chain is a functor.
Okay.
And the way they use this complex is to define a new functor, which they denote by T.
Oh, okay.
And T is the convolution of that complex.
Okay.
And that convolution, that's the functor that gives them the derived equivalence thereafter.
So wait, we start with functors, build this whole complex, and then, like, poof, out pops the equivalence.
Well, it sounds a little like magic, but, there's a lot of math behind each step.
Yeah, I bet. So it's all very carefully constructed.
Exactly. And the whole construction is actually a mirror of something from representation theory, the Rickard complex, is categorifying this decomposition of the reflection element in SL2.
Wow, that's amazing. It all ties together.
Yeah.
All right, well, before we get too deep in the weeds there, let's talk about these magic window categories.
Okay, sure.
So how do they offer a different way of looking at this derived equivalence?
Well, they provide a framework for understanding these equivalences for spaces that can be viewed as GIT quotients.
And, those cotangent bundles we've been talking about, those are actually GIT quotients.
Right. And these windows, they act as filters.
Okay.
They select certain objects in this derived category of matrix factorizations, and they do that based on special weight conditions.
Okay, so they kind of narrow our focus.
Exactly. It's like having these adjustable blinds. You can control how much light is let through, or in this case, which objects.
I like that. It's a good visual.
And the specific window equivalence that they're interested in, they call it Dibber, and that's connected to the interval this.
Okay.
And that interval determines the weight conditions.
So it tells us which objects are in and which are out.
Precisely.
So it's like setting boundaries for our window.
Yeah, exactly. And surprisingly, This specific window turns out to be really important.
Oh, okay. How so?
Well, it's the key to understanding this whole derived equivalence that we've been talking about.
Okay, and that brings us to the main theorem in the paper, right?
Right.
So what does it say about this connection between the window equivalence and all the other stuff we've talked about?
Well, the theorem states that the twisted equivalence, eton, which actually incorporates Knörrer periodicity, is it's the same as our window equivalence would.
Wait, are you serious? So all that stuff with the Rickard complex and the SL2 actions can all be understood through this idea of a magic window?
Yeah, that's pretty much what they show. It's like they found a shortcut.
That's incredible.
Yeah, it's pretty cool.
Okay, so we need to understand this Knörrer periodicity thing to really appreciate this.
Right.
So can you give me your refresher on Knörrer periodicity?
Yeah, so think of it like you've got two sets of blueprints, okay?
Okay.
One describes a skyscraper, and the other one describes, like, a big park.
Okay.
Knörrer periodicity is like a magical translator that lets you perfectly convert one blueprint into the other.
So it lets us move between these two different descriptions.
Exactly. And in this case, it lets us translate kernels, which are sheaves, into the language of matrix factorizations.
Okay.
And that's important because magic window categories are naturally defined using those matrix factorizations.
So it's like we need to switch dictionaries to understand the same story.
Right, exactly. And this is where those spaces, Willem and W. Kalak, come in, along with their structure sheaves.
Okay.
They provide, like, the recipe for the translation.
Okay, so now we've got our translated kernels, but how do we know this all makes sense?
Well, that's where the explicit computations come in. They show how those structure sheaves are actually transformed under this Knörrer periodicity map. It's pretty delicate, but it makes sure that the translated kernels actually have the right properties to, induce the functors we want.
Okay, so like checking to make sure that each word has been translated correctly.
Exactly. And there's another thing they check too. Remember those Landau-Ginzburg models? Well, those are spaces with this special function called a superpotential that kind of governs how everything behaves. The computations also make sure that the translated kernels are compatible with those superpotentials.
Okay, so it's like making sure they're playing by the rules in that new mathematical environment.
Yeah, exactly. And this whole process of translating and checking, it's super important for the proof. But there's one more thing. Remember, the window equivalence, Dubo, is actually defined on a larger space than where those kernels are initially defined.
Okay.
So to compare everything directly, we need to lift those kernels to that larger space.
It's like we need to zoom out to see the whole picture.
Exactly. And to do that, they have to relax some of those conditions that they initially put in place.
Okay.
It allows for more general maps and endomorphisms. And they introduce some new spaces, Wei, Ogé, and Jixi. Those capture the essence of what was happening before, but they're a little more flexible.
Okay, so we've zoomed out and expanded our view. How does this help us prove the main theorem?
Well, with those extended kernels, we can actually test if our convolution really acts like the window equivalence.
Okay.
We need to verify two things. First, we have to show that the convolution of these extended kernels, when you restrict it to the diagonal of x plus k AGLK, acts like the identity functor.
Okay.
And the second condition is that the essential image of the functor has to lie in that window subcategory W0NN.
Okay.
And what they show is that both of those conditions are actually met.
Wow, that's amazing.
Yeah.
So they wrangle all these abstract concepts into this really concrete proof.
Yeah, it's pretty cool.
It's incredible. Okay, but the paper doesn't stop there.
Right.
They also go into these grade restriction rules and this really interesting interpretation of the Rickard complex as mutations.
Yeah.
So what are those grade restriction rules all about?
Well, you can think of them as the bouncers at the entrance of our window club.
Okay.
They impose some constraints on what can actually be in the window subcategory.
So like a VIP section?
Yeah, exactly. And they're tied to this thing called the Kempfnis stratification, which, it's a way of organizing the objects based on their stability.
Okay, so it's all about maintaining order and making sure things have the right properties to be in that window.
Exactly.
And then how do these mutations fit into this whole thing?
Well, the mutations, they're the tools that we use to make sure that convolution follows those grade restriction rules.
Okay.
It's like you're sculpting something, you make small adjustments until you get the shape that you want.
Oh, okay. So the mutations allow us to fine-tune the convolution until it fits within those rules.
Exactly. And what's really cool is that the Rickard complex itself can be understood as this sequence of mutations.
Oh, wow.
Yeah. So each step in that complex actually corresponds to a specific mutation, and it's refining that kernel, making sure it fits in the window.
So it's like a series of small adjustments,
Yeah, precisely.
each one getting us closer to the final goal.
That's amazing. So understanding mutations actually helps us understand the Rickard complex even better.
Right.
'Cause it's all connected. This has been a mind-bending journey so far.
It really has.
Unpacking this paper, seeing how these ideas connect.
Yeah,
It's incredible.
it is.
And we're not even finished yet. There's still a lot more to explore.
There is. We've got the proof of the main theorem to go through and those corollaries.
Right. There's a lot more ground to cover.
Yeah, we've got plenty more to unpack.
Okay, so let's dive into this proof of the main theorem.
Okay.
Sounds like it's going to be quite a journey.
It is. It is. So remember those two conditions we need to check to show that our extended kernels are doing what they're supposed to.
Right. They have to behave like that window equivalence.
Exactly. So the first one is all about showing that the convolution acts like the identity when we restrict it to that diagonal.
Right, like a round trip with no changes.
Right. And to show this, they really get into the nitty-gritty.
They look at how the convolution acts on a very specific object,
Okay.
which is the structure sheaf of a point on the diagonal of x plus k a g l k, xk or glk.
Okay.
And they basically show that it maps back to itself.
So it's like carefully tracing each step to make sure you end up back where you started.
Exactly. But that's just the first condition, right?
Right. What about the second one? Making sure it maps into the right window.
Exactly. The essential image condition for that W0n subcategory.
Right.
So for this part, they use a strategy involving those spaces, K, Angi, and Jite,
Right.
and they analyze how those spaces map to the larger space, X plus K, A, L, X, K, A, L.
Okay, so they're using these smaller spaces as kind of stepping stones to understand the bigger picture.
That's a great way to put it.
Okay.
Yeah, so by looking at how those spaces interact, they can track the images of objects under the convolution. And through a bunch of really clever arguments, they show that everything ends up in the right place.
Okay, so they really wrangle those abstract concepts into a really concrete proof.
They do.
Wow, that's amazing. Okay, so let's maybe shift gears a bit and talk about those corollaries.
Okay, sure.
You know, what do they tell us about this main theorem?
Right. Well, they uncover some really interesting stuff.
Okay.
They show us that there's even more structure going on than we might have initially thought.
Okay, cool.
Yeah, and so the first corollary, if you remember, talks about the square of the equivalence t's acting as a window shift autoequivalence.
Yeah, that sounds a little cryptic.
It is. It is. But what it means is that if you apply t twice, it's kind of like shifting that window along the weight axis.
Oh.
So imagine you're sliding that window filter we talked about before,
Okay.
and you're just moving it along, and the equivalence is preserved.
Okay, so it's like it's not just connecting these cotangent bundles, it's creating patterns within them as well.
Exactly.
That's pretty cool. And this shifting property, it sounds like it's related to something called a spherical twist.
It is.
I've heard that before, but I'm a little fuzzy on the details.
Yeah, well, spherical twists are these special autoequivalences in derived categories, and they play a really important role in understanding things like mirror symmetry.
Oh, wow. So this seemingly simple equivalence T is actually connected to this whole other world of really deep math.
Right, exactly. It's pretty cool.
Okay, so that was the first corollary. What about the second one? That one involves Schur functors, right?
Yeah, that's right. And the second corollary shows us that certain Schur functors stay the same under this equivalence.
Okay.
And, you know, Schur functors, they're ways to build vector bundles.
Right. Okay, so some of them are invariant under the equivalence.
Exactly. And that actually tells us that even though these cotangent bundles seem different, there are some underlying structural similarities that are preserved.
Okay, so it's like there are landmarks that stay the same, even though the landscape around them is changing.
That's a great way to put it, yeah. So we've talked about the proof, we've talked about the corollaries, but let's go back to that translation process for a minute.
Okay.
You know, the one that takes those kernels and moves them into the world of matrix factorizations.
Right, the one with the Knörrer periodicity.
Exactly. So what are the main steps involved there?
Yeah. Tell me more about how that works.
Well, like we said before, it's really all about that Knörrer periodicity.
Yeah.
And the paper shows how those spaces, Willem and Ware, along with their structure sheaves, are really the key to this whole process.
Okay, right. They're the bridge between those two worlds.
Exactly. But how do we actually build those spaces?
Yeah, what makes them so special for this translation?
Well, they're constructed as fiber products, and they capture the relationships between different maps and endomorphisms. And all of that is essential for defining those functors E and F in the categorical SL2 action.
So it's like piecing together a puzzle, making sure all those elements from the SL2 action fit together in those new spaces.
Exactly. And they don't stop there. They actually verify that those intertwining conditions, equations 12 and 14 in the paper, are still satisfied within these new spaces.
Okay.
And those conditions, they ensure that those translated kernels are still respecting the SL2 action.
So it's like making sure the translation is grammatically correct.
Right. And the paper actually provides these explicit computations, it's really nice, that show how those conditions are met.
Okay.
So it's really detailed and thorough.
So they're really making sure that every I is dotted and every T is crossed in this translation.
Yeah, exactly. And they go even further, showing how those structure sheaves, the ones attached to Wum and Knörrer, are transformed under the Knörrer map.
Okay.
And those computations, they're like checking each word in the translation.
Oh, yeah.
Making sure it still captures those subtle nuances.
So they're fine-tuning the translation to make sure it's not just accurate, but it's also elegant.
Right. And those computations also show us that the translated kernels fit into those Landau-Ginzburg models we were talking about earlier.
Oh, right. The ones with the super potential.
Exactly.
Right.
They're making sure that everything is compatible.
So it's like checking to make sure that our translated message doesn't accidentally introduce any plot holes into the story.
Yeah, that's a good way to think about it. And this attention to detail is really important when it comes to extending those kernels to larger spaces. Remember, we needed to zoom out.
Right, to that bigger space.
Yeah.
X plus K, A, G, L, K, A, K, X, K, G, L, K.
Exactly. So those extended kernels, they're actually crucial for proving the main theorem.
Okay, how so?
Well, remember those two conditions for window equivalences.
Yeah, the ones that test whether the convolution is really acting like the window equivalence.
Right, exactly. So they take those extended kernels and they analyze what happens when you apply the convolution on that larger space. And what they show is that both conditions are actually satisfied.
So it's like those extended kernels provide the missing puzzle pieces that let us see the whole picture.
Exactly. And that's how they prove that the twisted equivalence is really the same as that window equivalence. It's a pretty amazing result.
It is. So they've connected these two seemingly disparate areas of math, the categorical SL2 actions and the magic window categories.
Yeah. It was like they found the secret passage between them.
It's really cool how these different ideas come together.
It is. And it really shows the beauty of math.
It does. Okay, well, we've covered a lot of ground here, but we're not quite done yet.
We're not.
We still have to talk about those grade restriction rules and the whole idea of the Rickard complex as a sequence of mutations.
Yeah, those are really fascinating ideas that deserve some more attention.
You do. All right, so let's dive into those next.
Yeah.
All right, so let's unpack these grade restriction rules.
Okay, sure.
It sounds like they're kind of like a quality control measure, making sure only certain objects are allowed into that window subcategory.
Right, exactly. Remember that Kempfness stratification? Well, it's kind of like sorting all the elements in the window by their stability, creating a hierarchy.
Okay.
And the grade restriction rules, they tell us which levels of that hierarchy are actually allowed in the window.
Okay, so it's setting a threshold. Only the most stable objects get in.
Yeah, you got it. And they also make sure that everything in that window subcategory, W0n, has weights that fall within a specific range from 0 to n.
Okay, so it's all about keeping things organized and consistent within the window.
Right.
But how do these mutations fit into all of this?
Well, mutations are the tools we use to actually make sure the convolution obeys those grade restriction rules.
Good.
Think of it like sculpting. You make small adjustments until you get the shape you want.
So you're saying mutations let us tweak the convolution until it fits within those rules.
Exactly.
Okay, I see. Now, earlier you mentioned something really interesting, the idea that the whole Rickard complex can be thought of as a sequence of mutations.
Right, yeah.
Can you expand on that a little bit?
Sure. So it turns out that each step in that complex actually corresponds to a specific mutation.
Oh.
And that mutation is basically refining the kernel, making sure it satisfies those grade restriction rules for the window.
So the Rickard complex, which seemed so complicated before, is really just a series of these small steps, each one shaping the kernel to fit the window.
That's a great way to put it, yeah.
Wow, that's a much more intuitive way to think about it.
It is pretty cool.
So understanding mutations really helps us understand the Rickard complex even better.
Exactly. It's all connected.
So stepping back a bit, What are the bigger implications of this work? We've explored all the details, but how does this research actually impact other areas of math? Maybe even physics?
That's a great question. This work touches on a lot of different areas. Let's start with representation theory, which is really at the heart of this paper.
Right, they use a lot of SL2 representation theory, right?
They do. And what's really cool is that this research provides a very concrete geometric way to look at SL2 representations. It connects that abstract algebra to the world of geometry.
So it's like seeing those abstract ideas come to life in a visual way.
Exactly. And this could lead to new ways of understanding and visualizing those representations,
Okay,
which is really exciting for anyone working in representation theory.
that's pretty remarkable.
Yeah.
What about connections to other parts of geometry?
Well, this work also sheds light on moduli spaces.
Okay.
Those spaces that parameterize geometric objects. And the cotangent bundles of Grassmannians, those are examples of moduli spaces.
Right.
And this paper is all about exploring the relationships between them.
So it's like mapping out the connections within this huge world of moduli spaces.
Right. And understanding moduli spaces is really important in lots of different fields, like algebraic geometry, topology, and even mathematical physics.
Okay.
Speaking of physics, you mentioned string theory and mirror symmetry earlier.
Yeah, I was wondering about that.
Well, those ideas are definitely lurking in the background here.
Okay.
Mirror symmetry, especially, is this incredible duality that connects different geometric spaces. And the equivalences we've been talking about, especially those related to magic window categories, they actually share some similarities with mirror symmetry.
So it's like seeing hints of nearer symmetry in the world of derived equivalences.
Exactly. And this could lead to a deeper understanding of mirror symmetry itself, connecting those abstract constructions to the physical realities of string theory.
Wow, that's amazing. It sounds like this research is opening up all sorts of new possibilities.
It is, and that's one of the most exciting things about math, discovering those unexpected connections and pathways.
Before we wrap up, can we go back to that conjecture at the end of the paper?
Oh yeah, the one about the simpler way to construct the window equivalence when K foo.
Right, the one that might let us bypass the Rickard complex entirely.
Yeah, that's a really interesting one. If that turns out to be true, it could be a real game changer. It would give us a much more direct and elegant way to understand these equivalences.
So it's a potential seed for future breakthroughs.
Exactly. It just goes to show you that even in the most abstract areas of math, there's always something new to discover.
That's true. Well, this has been an incredible journey.
It really has.
Exploring this paper with you, seeing how these different ideas fit together.
I agree.
It's been a real privilege.
It's been a pleasure.
And who knows what other amazing discoveries are waiting out there for us in the world of mathematics.
Exactly. The adventure continues.